Hey guys, good evening and welcome back again to your Unacademy NEET English channel. I hope all of you are doing great, having a good time. So my dear students, quickly, just let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Quickly guys, let me know in the chats. Everyone in the chats. Welcome back people, welcome back. Give me some green signal from the chats if I'm perfectly audible, visible to you. Perfect. Wonderful, guys. So, my dear students, as you all must be knowing, tonight we are going to start one more chapter, which is, again, I must say, one of the most important chapters of your chemistry. Because this chapter is directly linked with one more chapter of your chemistry, that is thermodynamics, right? Perfect. So, your thermodynamics becomes complete only if you have strong command on this particular chapter, which is states of matter, or you can call it as the gaseous state as well. Okay. And as I keep on doing always, I'll be starting exactly from the basics, from the scratch. I'll be assuming that you have never studied this chapter before, right? So from the scratch and slowly, we'll be scaling up the level as well, right? It is just, I would want you guys to take a note of every single thing. Whatever I'll be mentioning on the screen, whatever I'll be writing on the screen, I would want all of you to take a note of every single thing, my dear students. Yeah? Someone is asking, sir, molality and molarity you did not teach in mole concept. Yes, I did not teach concentration terms in mole concept. That will be done in the chapter solutions. Okay? You need not to worry. When I'll be teaching you the chapter solution, concentration terms will be the first topic from which I'll be starting with basically. Yeah? Perfect. So people, before starting the session, the ones who have not liked the session yet, I would want every one of you to like the session. Share this particular video with everyone. Whosoever is preparing for NEET 2024 or even 2025, this particular session is for everyone, right? And at the same time, the ones who have not subscribed to your Unacademy NEET English channel yet, I would want all of you to subscribe to the channel right now, right? Yes? So people, ready for the session? All are super duper excited about the session. Quickly, let me know in the chats. Then only we'll be starting. Quickly, my dear students, let me know in the chats if all of you are again super duper excited about this particular session, right? Give me some thumbs ups in the chat so that I'll get to know actually all of you are super duper excited for this particular session. Quickly in the chats with the thumbs ups. Quickly in the chats with the thumbs ups. Perfect, guys. Perfect, wonderful. All right then. All right, people. I hope the screen is perfectly visible to you, right? So, my dear students, I'll be starting this chapter exactly from the basics as I told you, right? So first, we are going to talk about some basic terminologies which are frequently used in this particular chapter. And what those basic terminologies are, let's get to know them one by one. The first basic terminology with which we are starting the chapter that everyone would have heard, I'm sure, that's pressure, right? Now, my dear students, if I ask you, how do we define the term pressure? How do we define it exactly? Well, let me exactly show you what is meant by the term pressure, which is denoted by P. And how do we write it? We write it as F divided by A. And what is meant by this F divided by A? Let's get to know about that as well. So have a look exactly what I'm going to talk about now. Understand exactly from the basics. Imagine, my dear students, I have got one container over here. Imagine this is one container which is closed on all the sides. The container is absolutely closed on all the sides. Now, dear students, let's imagine that there are some gas molecules present in this particular container. Imagine that there are some gas molecules in the container. Okay. Now, as you must be knowing, as far as the property of gas is concerned, gas molecules, they are always in continuous random motion. These molecules will be continuously moving in random directions, right? Okay. So these gas molecules, they are not static. They are in continuous random motion right now in the container. Now, dear students, if I select one of the wall of the container, let's say I'm selecting this particular wall of the container, right? I'm assuming the area of cross section of this particular wall, for example, that is 5 centimeters square. Let's assume the area of cross section of this particular wall over here, it's 5 centimeters square. Now, what exactly I'm doing? I'm going to divide this side. I'm going to divide this wall of the container into 5 equal parts. I've divided the wall into 5 equal parts. Well, after dividing this particular wall into 5 equal parts, if I select one part, if I select this particular part of the wall, can you let me know what is going to be the area of cross section of this particular selected part? Can I say it's going to be 1 centimeter square? Absolutely. The area of cross section of this shaded part over here is going to be exactly 1 centimeter square. And my dear students, this 1 centimeter square area is something which I'm calling as the unit area. This is the unit area which I'm calling. Okay. Now, since we know these gas molecules, they are in continuous random motion. Can I say some of the gas molecules will be colliding this unit area as well? Absolutely. Some of the gas molecules will be colliding with the unit area of the wall of the container as well. And you must be knowing, when the gas molecule collides the wall, what it does, it exerts some force on the wall, right? That force exerted by the gas molecules, on this unit area of the wall of the container, what do we call that as? We call that as the pressure. So force exerted by the gas molecules on the unit area of the wall of the container, that's something which we call as pressure of the gas, right? I hope it's super clear to you. Now, my dear students, imagine there are more gas molecules in the container. If there are more gas molecules in the container, can I say the probability of number of collisions with this unit area will be more? Absolutely. If there are more gas molecules in the container, the probability of gas molecules to collide with this unit area will be more. So force exerted by gas molecules on this unit area will be more. And eventually, pressure of the gas will be definitely more. Right? I hope this is super clear to you. Okay? So what is pressure? Pressure is defined as the force exerted by the gas molecules on the unit area of the wall of the container. Number one. Number two, if I ask you, what about the SI unit of pressure? What about the SI unit of pressure? You all must be knowing the SI unit of pressure is basically Newton per meter square, or you call it as Pascal as well, right? You call it either as Newton per meter square, or you can call it as the Pascal. This is the SI unit of pressure. My dear students, in this particular chapter, I'll be using some other units of pressure as well. There are some other units of pressure as well, which I'll be frequently using in this particular chapter, right? And let me tell you the relation between the different units of pressure, which I'll be using in this chapter. Okay, do remember that. My dear students, do remember this particular result. 1 atm. Atm is one of the units of pressure. 1 atm is equal to 1.013 bar, which is equal to 1.01325 into 10 raised power 5 Newton per meter square, which is also equal to 760 mm of Hg, millimeter of mercury, which is also equal to 760 torr as well. This is the relation between the different units of pressure, which I'll be frequently using in this particular chapter. Okay, so what is pressure? Pressure is the force exerted by the gas molecules on the unit area of the wall of the container, right? The SI unit of pressure is Newton per meter square, or you call it as the Pascal. The other units of pressure, which I'll be frequently using in this chapter, that's atm, that's bar, that's torr, that's Newton per meter square, that's mm of Hg, right? These are the different units of pressure which I'll be using in this particular chapter, even in thermodynamics, right? And my dear students, this is the relation between the different units of pressure which I would want all of you to remember from now onward. Okay? So this was our first basic terminology, that is pressure, right? And by the way, if you want the handwritten PDF of this particular session, right after the session, I'll be sending you the PDF. You'll be getting the PDF on this Telegram, t.me/WASSIMSIRCHAM, right? This is the Telegram channel, right, on which I'll be sharing the PDF right after the session, the handwritten PDF, okay? Perfect. So this was our basic terminology number 1. Now, talking about the basic terminology number 2. What is that? That is volume. If I ask you, how do we define the term volume? I'll just write its definition. I'm not going to explain a lot about volume right now, right? When I'll be teaching you the real gas part in this chapter only, there I'll be defining the volume. There I'll make you understand exactly the term volume. But right now, I'm just going to write its definition, okay? Volume of the gas, how do we define it? It is defined as the free space available for the gas. The free space available for the gas molecules. The free space available for the gas molecules to move. Now you must be thinking, what does that mean? Free space available for the gas molecules to move. That's called as volume? Yes, that's called as volume. This is something which I'll be teaching you in this chapter only when I'll be dealing with the real gas part over it, right? Now, dear students, my point here is to tell you the units of volume basically, which I need over here in this chapter. Units of volume, that's important, okay? What volume is, how do we define it? That will be discussed afterwards, okay? First thing, talking about the SI unit of volume. The SI unit of volume is nothing, it is meter cube. This is the SI unit of volume. There are some other units of volume as well, which we will be frequently using in this chapter. And let me quickly write the relation between the different units of volume. I'm right now talking about the other units of volume, which we want in this chapter. Do remember, 1 decimeter cube is equal to 1 liter, which is equal to 1000 centimeter cube, which is equal to 1000 milliliters, which is also equal to 1000 cc. And this cc over here, it stands for cubic capacity. The cc stands for the cubic capacity. This is one more important thing which I would want all of you to take a note of, right? These are the different units of volume which we'll be frequently using in this particular chapter. Okay? So 1 decimeter cube is equal to 1 liter, which is equal to 1000 centimeter cube, which is equal to 1000 milliliters, which is also equal to 1000 cc. And cc over here, it stands for the cubic capacity, right? Dear students, what is the third important thing, the third basic thing which you need to know? You need to know the units of temperature as well. You need to know the units of temperature as well. As you all must be familiar with the fact, the SI unit of temperature. The SI unit of temperature, what is that? That's Kelvin. That's Kelvin, which is represented by K, right? But in this chapter, we'll be talking about the other units. We'll be talking about the other units of temperature as well. And what are the other units of temperature which we shall be using in this chapter? One is going to be degree centigrade and another one is going to be Fahrenheit. Degree centigrade and Fahrenheit. Now you must be knowing the relation between degree centigrade, Fahrenheit and Kelvin. So let me tell you one important result over here. What is that? Temperature in Kelvin is always equal to temperature in degree centigrade plus 273.15. This is one of the results. This is one of the results which relates temperature in Kelvin with temperature in degree centigrade. And my dear students, in the similar way, there is one more result which you need to remember as well. And what is that? That is temperature in degree centigrade divided by 5 is equal to temperature in Fahrenheit minus 32 divided by 9. This is one more result which connects which relates temperature in degrees centigrade and temperature in Fahrenheit, right? So these are two important results which I would want every one of you to know, to remember from now onwards, right? SI unit of temperature is Kelvin. Other units which we'll be using here, one is degree centigrade and another one is Fahrenheit, right? Temperature in Kelvin is equal temperature in degree centigrade plus 273.15. In the similar way, temperature in degree centigrade divided by 5 is equal to temperature in Fahrenheit minus 32 divided by 9. Okay, I hope this is clear to everyone. I hope this is clear to everyone. Perfect. My dear students, one more thing. One more thing. In this chapter, whenever I'll be talking about the amount of gas, do remember, I'll be representing amount of gas in terms of moles, or I'll be expressing it in terms of grams. And preferably, I'll be expressing amount of gas in terms of moles in this chapter, right? So, amount of gas will be expressed in terms of moles or grams, right? And preferably, I'll be using the terms moles of gas instead of grams of gas, right? This is one more thing which you should know over here, okay? Now, there are a few important graphs which you must know as well. Because in this chapter, we have got a lot of graphs basically, right? Some of you must have studied this chapter before also. So you must be knowing there are a lot of graphs involved in this particular chapter. So to understand the graphs without mugging them up, let's try to know few important graphs basically. Okay. My dear students, if I write an equation here as y is equal to mx, and what exactly I need to do? I want to plot a graph between y and x. I want to plot a graph between y and x for the equation y is equal to mx. Do remember, the nature of the graph between y and x for the equation y is equal to mx, it's going to be a straight line passing through origin, right? It's absolutely going to be a straight line passing through origin. Number one. Number two, what is this m over here? This m is what you call a slope of the curve. This is what you call a slope. And what is slope exactly? Slope is nothing, it is tan of theta. Now you must be thinking what this theta is. Theta is basically the angle which this curve makes with the positive x-axis in the anti-clockwise direction. So this is theta basically, right? So dear students, once you get the value of theta, you just have to take the tan value of that theta, you'll be getting the slope of the graph, right? Perfect. At the same time, one more thing. The theta over here is acute. The theta over here is acute, right? It's less than 90 greater than 0. It's acute. If theta is acute, can I say tan of theta, tan of acute angle will come out to be positive? Yes, tan of acute angle comes out to be positive. That means the slope over here is coming out to be what? It's coming out to be positive. As simple as that. Okay? For example, I have got the equation as y is equal to 5x. This is the equation. Y is equal to 5x. What exactly I need to do? Let's say I need to draw a graph between y and x. I need to draw a curve between y and x for the equation y is equal to 5x. Now you tell me, can I say this particular equation, y is equal to 5x, can I say it resembles with y is equal to mx? Yes, it resembles with y is equal to mx. Here y, x, m is equal to 5. So if this equation is resembling with y is equal to mx, so the nature of the curve over here between y and x, it's going to be a straight line only, right? Now if I ask you about the slope of this graph, about the slope, you will say slope is always represented by m. And m while comparing comes out to be 5. M while comparing comes out to be 5. So 5 is basically the value of tan of theta here, right? So you got to know tan of theta is nothing, it's 5. If tan of theta is equal to 5, that means theta over here has to be tan inverse 5. Theta has to be tan inverse 5. I hope you're following properly with me. Yeah? This is the first equation which you need to know. Y is equal to mx. Similarly, talking about the second equation. The second equation, for example, is y is equal to mx plus c. Y is equal to mx plus c. First of all, let me tell you this m over here. As I told you already, m is what we call a slope and c is what we call as intercept. C is what we call as intercept. Now, dear students, if you want to plot a graph, between what and what? If you want to plot a graph between y and x, if you want to plot a graph between y and this x, the nature of the curve is again going to be a straight line, but the straight line won't be passing through the origin. The straight line will be starting from above the origin like this. This is going to be the nature of the curve. Y is equal to mx plus c, right? The graph between y and x for the equation y is equal to mx plus c. Now, dear students, do remember one thing. The distance from the origin to the point from where the curve starts. That means the distance from here to here. The distance from the origin till the point from where the curve starts. That distance is represented by c over here, and this c is what we call as intercept, right? And at the same time, if you are talking about the slope of the curve, what is slope? Slope is tan of theta. Theta is the angle which the graph makes with the positive x-axis in the anti-clockwise direction. This is theta over here. Now, if I ask you whether this theta is again acute or obtuse, the theta over here again is acute, and tan of acute always comes out to be positive. That's why we say slope of this curve over here, that is tan of theta. Theta is acute, so therefore tan of theta will come out to be positive. So slope for this curve is positive as well. Okay, perfect. So this was the second graph. Similarly, my dear students, let's say we have got the equation y is equal to mx minus c. Okay, in this equation again we have got intercept c. Again we have got intercept. That means there will be a straight line, but the straight line won't be passing through the origin. It has to be either above from the origin or it has to start below from the origin. Now look at the sign of this c. C is negative over here. That means the straight line will be starting below the origin. C sign over here was positive. That's why the straight line was starting above the origin, right? But right here, the C sign is negative. So straight line has to start down the origin. Okay. So if you want to plot it, basically, you can plot it like this. Let's say this is Y. Let's say this is X, right? So let me extend this Y axis a bit. Let's say this is origin, right? The graph has to be a straight line, but the straight line has to start down the origin. Let's say it starts from here and it's going to be like this. Okay, perfect. Now people, the distance from the origin to the point from where the graph starts, that distance is what you call as intercept, which is basically this distance is C over here, right? Perfect. And at the same time, if you talk about the slope, slope is represented by m. M, you already know that's tan of theta, and theta is the angle which the graph makes with the positive x-axis in the anti-clockwise direction. Again, as you can see, theta is coming out to be positive. And if theta comes out to be positive, theta is coming out to be acute, right? Therefore, tan of theta will come out to be positive over here. That means the slope of the curve over here is positive again. Yeah, I hope it's clear. So over here, you had the positive intercept, and right here, you have got the negative intercept. As simple as that. Similarly, this was the what? This was the third graph, right? Now let's have a look on the fourth one. Let's say you have got the equation in this format. Y is equal to minus mx plus c. I'm making all the graphs in the first quadrant itself, right? Because in chemistry, 99.9 graphs, 99.9% of graphs are made in the first quadrant itself. That's why I'm not using the other quadrants, right? Okay, y is equal to minus mx plus c. Make a graph. Make a graph between y and x. Can you do it? Make a graph between y and x. I'm sure you can easily do it. Now, first of all, have a look. Is the slope here positive or negative? Slope is negative. Slope is negative means tan of theta is negative, right? So first of all, we got to know that slope is negative. What does that mean? That means tan of theta is negative. Tan of theta is negative means theta is coming out to be obtuse over here. Because tan of obtuse angle comes out to be negative. Number one. Is there intercept? Yes, there is intercept. So is the straight line going to be passing through the origin? No way. There's the intercept. It has to start either above the origin or below the origin. Now look at the sign of this C. It's positive. That means the straight line has to start above the origin. So straight line, for example, will be starting from here, above the origin. Now we have to show the negative slope. So the graph has to be like this, so that this angle will come out to be obtuse, which is theta. Perfect. Simple. Y is equal to minus mx plus c. This was our fourth graph. Similarly, if I talk about the fifth graph, let's say you've got the equation in this format. Xy is equal to k, or you can write it like this. Y is equal to k divided by x. Perfect. And I want you guys to plot a graph between y and x over here. I want you guys to plot a graph between y and x over here. My dear students, just tell me one thing, whether this y and x are directly proportional or inversely proportional to each other. Look at the equation. Y and x, they are inversely proportional to each other. Whenever you need to make a graph between two variables which are inversely proportional to each other. Whenever you need to make a graph between two variables which are inversely proportional to each other. Do remember, the nature of the curve is going to be rectangular hyperbola. And this rectangular hyperbola, it neither touches the y-axis nor it touches the x-axis. And I'm making the graph only in the first quadrant itself because we need only this much, nothing else. Okay? So do remember, whenever we need to plot a curve between two variables which are inversely proportional to each other, the nature of the curve always is going to be the rectangular hyperbola. So you call this particular graph over here as, you call it as the rectangular hyperbola. I hope this is super clear to you, right? Similarly, dear students, let's have a look on the sixth equation. For example, you have got the equation in this format. Let's say you have got the equation in this format. Y is equal to kx square. Y is equal to kx square. And let's assume you have to make a graph between y and x. You have to make a graph between y and x for the equation y is equal to kx square. The nature of the graph is going to be parabola opening upwards. It's going to be basically parabola opening upwards. But since I'm making the graphs only in the first quadrant, so I'll be only keeping this part. That's it. Right? Otherwise, it's like this. Otherwise, it's like this. Right? And this particular curve is what we call as, what do we call this as? Parabola. Parabola opening upwards. This is parabola opening upwards, right? This was our sixth graph, y is equal to kx square. There are two more graphs which we need in this chapter. Let's have a look what those are exactly. For example, you have got the equation. I think this is the seventh one now, yeah? This is the seventh one. Let's say you have got the equation as y is equal to k e raised power x. Y is equal to k e raised power x. Okay? Let's say somewhere you find this sort of an equation. Y is equal to k e raised power x. And you have to plot a graph. You need to plot a graph between y and x over here. You need to plot a graph between y and x over here. Right? Perfect. The graph will come somewhere from here and it will exponentially increase. So I'll just make the first quadrant part. So it has to be like this. What's happening here? So it has to be like this. It is something which we call as exponential increase. This is the exponential increase curve. Y is equal to k e raised power x. Okay. Similarly, the last one which we need in this particular chapter, the equation is y is equal to k e raised power minus x. Right? Y is equal to k e raised power minus x. Let's say you need to plot a graph between y and x. You need to plot a graph between y and x over here. Basically, the graph will come somewhere from here and it will pass like this, right? So I'm only making the first quadrant part. Let's say it's passing through this point. So it's going to be like this, right? So, and this particular graph is something which you call as exponential decrease. This is something which you call as exponential decrease. Perfect. These are some very important graphs which you must know before starting the chapter. I hope every single thing is clear till here. Let me know quickly in the chats if all the things are clear. Quickly, people. Quickly, everyone. Let me know quickly in the chats if every single thing is clear till here. Yeah? All the graphs are perfectly fine? I hope all the graphs are perfectly fine for you. Starting with y is equal to mx, straight line passing through origin. Y is equal to mx plus c, right? Y is equal to mx minus c. Y is equal to minus mx plus c. Then you have got xy is equal to k. Then you have got y is equal to kx square. And at the same time, y is equal to k e raised power x, y is equal to k e raised power minus x. Right? These were some important graphs which we need in this chapter. Now, dear students, since the basic things which we needed in this chapter, I have covered them. Okay? I have covered the basic things. Now, it's time to actually enter into the chapter. Now, we are going to enter into the chapter, my dear students. Okay? Now, we are going to enter into the chapter. All right. So, let's have a look now. The first topic which we are going to cover here in this particular chapter. What is the name of the topic? It's very simple, but understand properly. Okay? The topic name is Boyle's Law. Right? Boyle's Law. First of all, let me write the statement of the Boyle's Law. Then I'll make you understand what this Boyle's Law exactly is all about. Okay? It has got a very simple and basic statement. The statement is something like this. The statement is, let me write it over here. For a fixed amount of gas, for a fixed amount of gas at constant temperature, for a fixed amount of gas at constant temperature, pressure of the gas is inversely proportional to the volume of the gas. Pressure of the gas is inversely proportional to the volume of the gas. Okay? Before making you understand this particular statement, I'm going to write it in the mathematical formulation. So Boyle's law states that the pressure of the gas, it's inversely proportional to what? It's inversely proportional to volume of the gas. But under a condition, and the condition is number of moles and temperature of the gas has to be constant. Has to be constant. Now let's have a look what exactly this statement means. Let's have a look what exactly this statement means. Okay, let's have a look, people. Have a look and understand. For example, I'm taking one container over here. Let's say this is one container, which is closed on all the sides. On the top of the container, for example, you have got the piston. You have got the piston on the top. The piston can go up, it can come down as well, right? And you can easily imagine when the piston goes up, what happens to the volume of the container? Volume of the container increases. When the piston comes down, what happens to the volume of the container? When the piston comes down, volume of the container decreases. As simple as that. Now, my dear students, I am going to keep some ideal gas molecules inside this particular container. I've kept some ideal gas inside the container. Now, you tell me whether the container is closed on all the sides or not. Yes, the container is closed on all the sides. That means whatever gas I have kept inside the container, it's not going to come out. Whatever gas I have kept inside the container, it's not going to come out at all. Right? Perfect. So what does that mean exactly? That means I'm keeping the number of moles of the gas constant. I'm not going to let the moles of the gas to change. Right? No leakage at all. I'm not going to let the moles of the gas to change. Number one. Number two, I'm going to keep the temperature of the gas constant as well. And why is that? Why did I keep moles and temperature of the gas constant? Because the law which we are going to deal with, this Boyle's law, it is only applicable to the ideal gas if the ideal gas is present at constant moles and temperature. Right? If the moles of the gas and temperature of the gas is kept constant, if we are not supposed to let the moles and temperature of the gas to change, then only we can use Boyle's law for the gas which we have taken in the container. Now, what does this law say? The law says that pressure of the gas is inversely proportional to volume of the gas, which is evident. If you increase the volume of the gas, the pressure of the gas will decrease. If you decrease the volume of the gas, the pressure of the gas will increase. Why it happens? It's simple. My dear students, remember one thing for now. Remember one thing for now. Do remember, volume of the ideal gas is always equal to the volume of the container. Volume of the ideal gas is always equal to the volume of the container. You must have studied also. An ideal gas occupies the volume of the container in which it is kept, right? An ideal gas, it occupies the same volume of the container in which it is kept, right? Dear students, you tell me one thing. So in short, what we have to remember, volume of the ideal gas is always equal to volume of the container, right? Now understand. For example, if the piston goes up, what is happening to the volume of the container? Volume of the container is increasing. And if the volume of the container increases, can we say volume of the gas increases? Because ideal gas occupies the volume of container in which it is kept. If the volume of the container is increasing, that automatically tells you that the volume of the gas is increasing. So we are lifting the piston up. That means we are increasing the volume of the gas. And when we are increasing the volume of the gas, can you tell me what will happen to the distance between the molecules? Can I say distance between the molecules will also increase? And if the distance between the molecules increases, what will happen to the number of collisions inside the container? Can I say number of collisions inside the container will decrease? And if the number of collisions inside the container decreases, what will happen to the pressure of the gas? The pressure of the gas will automatically decrease. So on increasing the volume of the gas, the pressure of the gas decreases. Similarly, if you bring the piston down, the volume of the container decreases. Volume of the gas decreases. The gas molecules come closer, due to which collisions increase. And if collisions increase, that means pressure automatically increases. So what Boyle's law says, first statement which you need to know all the time, Boyle's law is applicable to an ideal gas only if number of moles and temperature of the gas is kept constant. And as far as the Boyle's law is concerned, pressure of the gas is inversely proportional to what? Pressure of the gas is inversely proportional to the volume of the gas. Number one. Now people have a look on the second thing. If I remove this proportionality sign, I'll be getting a constant over here. Constant K divided by V. Let me tell you, this K over here, it is something which you call as Boyle's constant. This K over here is something which you call as Boyle's constant, right? Now you must be thinking, what is the value of this Boyle's constant K? You must be thinking, what is the value of this Boyle's constant K? My dear students, have you ever studied the ideal gas equation? I'm sure you would have. Ideal gas equation says P is equal to nRT divided by V, right? And as far as the Boyle's law is concerned, what kind of equation did we get? We got this equation, P is equal to K divided by V. These are the two equations which I wrote. One, the ideal gas equation. Another one as far as the Boyle's law. Now, when you compare these two equations, this is pressure here, this is pressure. This is volume, this is volume. That means this K automatically becomes equal to what? K automatically becomes equal to nRT. So my dear students, do remember the value of Boyle's constant from now onwards. It is equal to nR multiplied by T. I hope it's clear to everyone. The value of Boyle's constant is equal to nRT. Okay, number one. Number two, if I just cross multiply things, I'll say P multiplied by V is equal to constant. And it's only valid when number of moles and temperature of the gas is kept constant. Correct? There is a significance of this particular equation as well. This equation has got significance. What does it mean? What this equation tells us? This equation tells us that when the ideal gas is kept at constant moles and temperature, when the moles and temperature of the gas is kept constant, the product of pressure and volume of the gas, it always comes out to be constant. What does that mean? Let's have a look. Imagine that the gas in the container, let's say its pressure, for example, is 10 atm. Let's say its pressure is 10 atm. And when the pressure of the gas is 10 atm, let's assume its volume is 5 liters. When the pressure of the gas is 10 atm, its volume is, for example, 5 liters, right? So at this particular point of time, when the pressure of the gas is 10 atm, its volume is 5 liters. If I take the product of two, can I say the product of two will come out to be 50, 10 multiplied by 550, right? Now, my dear students, what exactly I'm going to do? I will change the pressure of the gas. Let's say I'm decreasing the pressure of the gas from 10 atm to 5 atm. I'm decreasing the pressure. I'm decreasing the pressure. And as far as this particular result is concerned, when you decrease the pressure, volume will eventually increase. Since we are decreasing the pressure, so volume will eventually increase, and it will increase in such a way, that the product of pressure and volume again comes out to be 50 only. The product of pressure and volume again comes out to be 50 only, right? So this is the significance of the equation. Boyle's law says, when number of moles and temperature of the gas is kept constant, the product of pressure and volume does not change at all. If you change the pressure, volume will accordingly change in such a way that the product of pressure and volume will remain fixed. Its value won't change at all, right? Perfect. So in short, can I write it like this? If this is clear, can I write it like this? Let's say when the pressure of the gas was P1, its volume was V1, right? And when the pressure of the gas was P2, its volume was V2, right? Now, as far as Boyle's law, P1 multiplied by V1 has to be K, P2 multiplied by V2, it has to be equal to the same K. Now, looking at these two equations, can I say P1 V1 has to be equal to P2 V2? So this is the equation which I'll be frequently using in the questions. And do remember this particular equation I'll be using only when number of moles and temperature of the gas is kept constant. I hope it's super clear to you. Let me know quickly in the chat. Let me know quickly in the chats, my dear students. Let me know quickly in the chat. Quickly. Yeah? Done? Simple? Absolutely. Now, my dear students, there are some important graphs which are related to the Boyle's law. And let me teach you exactly how those graphs are made related to the Boyle's law. There are a lot of graphs basically which are related to the Boyle's law. Let's have a look what kind of graphs can we make over here. Okay. So we are going to make certain graphs over here. So let's have a look how these graphs exactly are made. Let's have a look how these graphs exactly are made. This is going to be our first graph. Okay, let's keep it as such. Similarly, this is going to be our second graph. Let's make 4 graphs in the beginning. Then we'll see how many other graphs can be formed. Okay. Now, people, let's try to make certain graphs related to Boyle's law. The first graph which I'm going to make, that's going to be between pressure and volume. Pressure and volume of the gas. Since we are going to draw the graphs related to the Boyle's law, right? So what is the basic equation as far as the Boyle's law is concerned? Boyle's law says that P is equal to K by V. Correct? P is equal to K by V. Now, my dear students, this pressure over here, I'm plotting along y-axis. And volume here, I'm plotting along x-axis. Pressure, I'm plotting along y-axis. Volume, I'm plotting along x-axis. So this P over here, I'm plotting along y-axis is equal to K divided by V, I'm plotting along x-axis. Now, a few minutes back only I told you, whenever you need to draw a curve between two variables which are inversely proportional to each other, the nature of the curve is going to be rectangular hyperbola. So it has to be rectangular hyperbola. And this rectangular hyperbola is made when temperature of the gas was kept constant. It was made when temperature of the gas is kept constant. And this particular hyperbola over here is what you call as, something which you call as isotherm. So this is the first graph which is related to Boyle's law. Number 1. Okay. Number 2. Let's try to plot one more graph between pressure of the gas and 1 by volume. 1 by V. P versus 1 by V. Since again we are drawing a graph related to the Boyle's law, so I'll be using the basic equation which says P is equal to K by V. Or you can write it as P is equal to K multiplied by 1 by V. You can write it like this as well. No issues at all. Yeah. Now, dear students, this pressure you are plotting along which axis? Along y-axis. This pressure you are plotting along y-axis. And this 1 by V you are plotting along x-axis. Now, along x-axis you are not plotting volume. You are plotting 1 by volume. Right? So, in this particular equation, this P you are plotting along y-axis is equal to 1 by V, this whole term you are plotting along x-axis. So, this K becomes your M, right? And Y is equal to mx. What is it going to be? It's going to be a straight line passing through origin. As simple as that, right? Straight line passing through origin. The second graph. Similarly, talking about the third graph. For example, you need to draw a curve between PV versus V. PV versus V. Product of pressure and volume versus volume. Few minutes back I told you, on changing the volume of the gas or on changing the pressure of the gas, what will happen to the product of pressure and volume? Will the product of pressure and volume change? Will the product of pressure and volume change? On changing the volume or on changing the pressure, will the product of pressure and volume change? Few minutes back I told you, the product of pressure and volume is not going to change, right? If you change the volume, if you increase the volume of gas, or if you decrease the volume of the gas, nothing is going to happen to the product of pressure and volume. It's going to be independent, straight line. Yeah, straight line. Similarly, if I want to plot a graph between PV versus P, if I increase or decrease the pressure of the gas, nothing happens to the product of pressure and volume. It's again independent only, right? It's again independent only. Nothing is going to happen to it, right? Few more graphs, my dear students, related to Boyle's law. Let's have a look. For example, I need to make a graph between P by V versus 1 by V ka square. P by V versus 1 by V ka square. This is one of the curve. Similarly, let's make one more curve. That's going to be between P by V versus 1 by V. P by V versus 1 by V, right? Similarly, at the end, let's try to draw one more graph, which is going to be between log of P versus log of P. Let's see how exactly we are going to get the equations, how exactly we are going to get the graphs. Understand? My dear students, over here, along your y-axis, what you are plotting P by V. Along x-axis, you are plotting 1 by V ka square. Since the graph is related to the Boyle's law, so I shall be using the basic equation. And the basic equation, you know it, P is equal to K divided by V. Or you can write P is equal to K multiplied by 1 by V. Correct? But dear students, if you exactly have a look, along y-axis, I'm not plotting pressure. I'm plotting P by V. But over here, we have got P. Right? In this equation, we have got P. But I'm not plotting P there. I'm plotting P by V. So what I'm doing, I'll be dividing this equation throughout by volume. If I divide this equation throughout by V, it becomes P by V is equal to K 1 upon V ka square. Right? Clear? Now this P by V over here, this P by V, since I'm plotting along y-axis, is equal to 1 by V ka square. 1 by V ka square. I'm plotting along x-axis, so this K has to be M. Y is equal to mx. What is going to be the nature of the graph? The nature of the graph is again going to be a straight line. Right? Isn't it simple? Absolutely, it's damn simple, right? Y is equal to mx. And one more thing, if I ask you, what about the slope of this curve? What about the slope of this curve? Slope means M. And M value over here, when you compare these two equations, M value is equal to K. So slope of this curve is equal to K. Right? Slope of this curve is equal to K. And K already we know, as per Boyle's law, K is nothing, that's nRT. Yeah? Simple. Now, dear students, have a look on one more graph. Over here, along y-axis, you are plotting P by V. Along x-axis, you are plotting 1 by V. Correct? Use the basic equation. P is equal to K multiplied by 1 by V. This is the basic equation. Right, P? Now, dear students, along y-axis, I'm plotting P by V. But over here, we just have P. So, I'll be converting this equation in the format of P by V. So, dividing this equation throughout by volume. Dividing it with volume, so it becomes square. Right? Yes? Perfect. Now, my dear students, if you look at this P by V, this P by V, you are plotting along what? You are plotting along y-axis is equal to. Only 1 by V you are plotting along x-axis. Only this 1 by V you are plotting along x-axis. So instead of just 1 by V, I'm writing x, right? But this is 1 by V ka square. So it's x square and this is k. Y is equal to kx square. What is the nature of the graph? It has to be parabola, opening upward, something like this, right? Perfect. Now, dear students, at the end, let's try to make a graph between log of P and log of P, right? Log P, I'm plotting along y-axis. Log V, I'm plotting along x-axis, correct? Right? So first of all, I'll be using the basic equation again, and the basic equation is simple. That's P is equal to K divided by V, correct? But I'm plotting log P along y-axis. But over here, we have got just P. So I need to convert this P into logarithmic form. And how exactly are you going to do that? I'll just multiply this equation throughout by log. So it becomes log of P is equal to log of K divided by V. Agreed? Yeah? Now, I can write it like this. Log of P is equal to, this is log of M by N, which comes out to be log of M minus log of N. Perfect? Or you can just reshuffle this equation. You can write it like this. You can write it as log of P is equal to, first you write minus log V. First you write minus log V. And after minus log V, you write plus log of K. It won't make a difference. Won't make a difference at all. Yeah? Okay. So dear students, log of P, you're plotting along y-axis. So instead of log of P, you're writing y is equal to log of V, you're plotting along x-axis. So instead of log of P, you're writing x. And this is minus over here. This is minus over here. And this is plus in between. Log K will be your C, right? And the value over here is 1, right? The value over here is basically minus 1. The value over here is minus 1 basically in the beginning. So can I say the equation resembles with y is equal to minus mx plus c? If the equation resembles with y is equal to minus mx plus c, the graph has to be like this. The graph has to be like this. Okay? If I ask you about the intercept, the distance from the origin to the point from where the graph starts, that means this distance I'm asking you. This distance means intercept, which is basically log of k. Intercept log of k, right? If you ask me, what about the angle? What about this particular angle? What about theta? If you ask me what about theta, I'll ask you, the slope of the curve is minus 1 basically. It's minus 1 here in the beginning, right? So slope is minus 1. That means tan of theta is equal to minus 1. When is tan of theta minus 1? When theta is equal to 135 degree. So this angle has to be 135 degree. I hope it's again clear to you. Yeah? Right? These were different types of graphs which can be asked, right, as far as the Boyle's law is concerned. Now, dear students, let me tell you a few more important things. Related to the graphs only. There can be one question asked from the graphs itself. From the graph only, there can be one question asked. For example, you are given with certain graphs like this. Let's say I'm plotting pressure along y-axis, volume along x-axis, right? Let's say there are 3 isotherms which are given to us. This one is made at temperature T1, this one is made at temperature T2, and this one it's made at temperature T3. These are 3 isotherms which are given to us. And there are few options given. You need to identify which temperature is more and which temperature is less. You need to see whether T3 is more than T2, more than T1, or you need to see whether T1 is more than T2, more than T3. How do we exactly check it? There is one general procedure which I would want all of you to follow from now onwards. My dear students, what is that general procedure? Have a look. First of all, always whenever you see this kind of the question, you'll be always drawing a straight line. You'll be always drawing one straight line. This is the straight line which I'm drawing. Yeah. After drawing the straight line, you'll be marking these points. After marking these points, you'll be getting the corresponding y-axis value. Get the corresponding y-axis value. And y-axis here is pressure. Corresponding to temperature T1, pressure has to be P1. Corresponding to temperature T2, pressure has to be P2. And over here, pressure has to be P3. Perfect. That means from here to here, it's P1. From here to here, it's P2. From here to here, it's P3. Now, if I ask you which pressure is more among all, can I say P3 is greater than P2, which is greater than P1? P3 is maximum, followed by P2, followed by P1, right? Now, you must have studied the ideal gas equation. Ideal gas equation says P is equal to nRT divided by V. Correct? Ideal gas equation says P is equal to nRT divided by V. My dear students, since you have drawn a straight line parallel to y-axis, that means you're keeping the x parameter constant. X parameter here is volume. So you're keeping volume constant. By drawing the straight line, you're keeping the volume constant. Number of moles at R was already constant. So can I say pressure is directly proportional to temperature in this case? Absolutely, pressure is directly proportional to temperature in this case. So more the pressure, more the temperature. More the pressure, more the temperature. T3 is more. That means T3 has to be more than that of T2, than that of T1. So this is the correct answer of the question, right? And these sort of questions are frequently asked basically nowadays. I hope it's super clear to you. Yeah? Right? Perfectly done? Okay, one more question. Let me see if you can solve this or not. For example, I'm giving you a question like this. I'm, for example, giving you a question like this. I'm plotting certain graphs between P and 1 by V. P and 1 by V, right? And you know already, the graphs are like straight lines, like this. This was made at temperature T1, this was made at temperature T2, this was made at temperature T3. Again, you need to identify which temperature is more and which one is less. How exactly you guys will do it? You'll be drawing a straight line. You'll be drawing a straight line, right? Parallel to y-axis. Now, mark these points where the straight line cuts. Get the corresponding y-axis value. Corresponding to temperature T1, the pressure has to be P1. This has to be P2. This has to be P3. Now, among P1, P2, P3, can I say P3 is greater than P2, which is greater than P1? Absolutely. Absolutely, right? P3 is greater than P2, which is greater than P1. Now, dear students, as far as ideal gas equation is concerned, P is equal to nRT divided by V. This is the ideal gas equation. Again, you are drawing a straight line parallel to y-axis. That means you are keeping the x parameter constant, and x parameter here is 1 by V. X parameter here is 1 by V. Now, if 1 by V is constant, that actually tells you volume is also constant, right? It's simple, right? If 1 by x is constant, what does that mean? That means x is also constant. Correct? So, by drawing the straight line, you are keeping the x parameter constant. You are keeping 1 by V constant, which is telling you that V is also constant. So, V is constant, number of moles are already constant. So, again, I can say pressure is directly proportional to temperature, right? So, more the pressure, more the temperature. Pressure is more at 3, so temperature has to be more at 3 as well. So, T3 greater than T2 greater than T1. I hope these sort of graphical questions you guys are easily going to solve from now onwards. Right now, I'm not going to show any sort of problem. Any numerical, I'm not going to show. Numericals, I'll only show you when I'll teach, I'll complete all the gas laws. Then it could be fun to solve the numericals in lesser time with the help of some shortcuts, right? So this was all about your Boyle's law. All the graphs are really important, right? All the things which I told you in the Boyle's law, they are very, very, very important. Now you tell me in the chats with the thumbs ups whether every single thing is clear or not. Quickly, my dear students. Then only I can move on. To the Charles law. By the way, this was question which was asked this year, NEET 2023. Can't you solve this question now? Which among us the following options is correct graphical representation of Boyle's law? Correct graphical representation of Boyle's law. You need to answer this. We just did this question. Correct graphical representation of the Boyle's law. P versus V, no doubt it's rectangular hyperbola, but it's showing T3 is greater than T2 greater than T1. We did this few minutes back. It's always this T1 will be more than T2 more than T3. This one, P versus 1 by V, straight line, yeah? And T3 will be greater than T2 greater than T1. So this is correct absolutely. This was your NEET 2023 question. Yeah, this was your NEET 2023 question, right? Similarly, one more same question which was asked in your NEET 2021. Look at the question and you tell me the answer. You tell me the answer. The graph is between pressure and volume. Is the pressure volume graph straight line? No. Is it straight line? No. Pressure volume graph is a rectangular hyperbola. So it can be either option C or option D. But few minutes back we saw that hyperbola which is at the top, that is always at higher temperature. That hyperbola which is at the top is always at higher temperature. So 600, 400, 200. Absolutely option C is correct. Right? Agreed? See, everything we are done. I mean, you can easily solve these questions now. Because few minutes back only we did this. All right, people. So let's have a look now on one more gas law, which is what you call as Charles' law. Right? Charles' law. So let's have a look what Charles' law states and why it's important. Let's have a look what Charles' law states and why exactly it's important. As far as Charles' law is concerned, again, let me write its statement. For a fixed amount of gas, at constant pressure, volume of the gas is directly proportional to the temperature of gas in Kelvin. This is the first statement of the Charles' law. Volume of the gas is directly proportional to the temperature of the gas in Kelvin. First of all, let me write its mathematical formulation, then I'll make you understand what exactly it means. Okay? Let me write its mathematical formulation. Volume of the gas is directly proportional to temperature of the gas in Kelvin. But this is only valid when number of moles and pressure of the gas is kept constant. What it means, you'll get the idea in some time. Before explaining you that, let's remove the proportionality sign. So it has to be V is equal to constant multiplied by temperature in Kelvin. Right? And this K over here, it is something which you call as Charles constant. Right? Now the point is, if I ask you, what is the value of this Charles constant? What is the value of this K over here? Again, you are going to use the same procedure. As per the Charles law, V is equal to K multiplied by T. As far as the ideal gas equation is concerned, can I say V is equal to nRT divided by P? This is basically the ideal gas equation, right? PV is equal to nRT. PV is equal to nRT. This is the ideal gas equation. Now, my dear students, look at these two equations and compare them. Over here, you have got volume. Right here, this volume. Temperature. That means this K has to be equal to nR divided by P. On comparing these two equations, we got to know K is equal to nR divided by P. So your K over here, it is equal to nR divided by P. Okay, this is your Charles constant. My dear students, in the similar way, I can write the equation like this. V divided by T is equal to constant. This is one more equation. Okay, and similarly, one more equation which I'm going to write. V1 divided by T1 has to be equal to V2 divided by T2. Now let's get to know the meaning of all these things over here. One by one, we are going to talk about all these things. Yeah? Let's see what it means. Imagine that this is the container. And my dear students, there is the piston fitted at the top of the container. The piston can go up, it can come down as well. Okay? Right? For example, I'm keeping some ideal gas molecules inside this particular container. These are the ideal gas molecules which I have kept inside the container. Now, my dear students, when can we use Charles' law to a particular ideal gas? Charles' law is applicable to an ideal gas only under certain conditions. When number of moles and pressure of the gas is kept constant. What does that mean? That means if you do not let the moles and pressure of the gas to change, if you do not let the moles and pressure of this gas to change, then only you can use Charles' law for this particular gas. So in order to use the Charles law for a particular gas, moles and pressure of the gas has to be kept. Has to be fixed. Number one. Number two. Since moles and pressure of the gas is kept constant, that means it will be following the Charles law now. And Charles law says that volume is directly proportional to temperature. What does that mean? That means if you increase the temperature of the gas, eventually volume of the gas will increase. Similarly, if you decrease the temperature of the gas, volume of the gas will decrease. Why is that? Why on increasing the temperature, volume increases? You must be thinking, right? Why on increasing the temperature, the piston goes up, volume increases? Why does that happen? See, it's simple. First of all, if you try to increase the temperature of the gas by supplying heat, if I supply heat to this gas, why? Because I want to increase the temperature of the gas. So on increasing the temperature of the gas by supplying heat, I say the kinetic energy of these molecules will also increase. By supplying heat, the kinetic energy of the molecules is increasing. And my dear students, if kinetic energy of the molecules will increase, they say the pressure of the gas will start to increase. If the kinetic energy of the gas molecules increases, that means the number of collisions will start to increase. Pressure will eventually increase. But do I have to let the pressure of the gas to change? I do not have to let the pressure of the gas to change. No doubt, I'm increasing the temperature, due to which pressure has to increase. But at the same time, in order to keep the pressure fixed, what will happen? On supplying the heat, the piston will eventually start going upwards, so that molecules go far, due to which the pressure remains maintained, right? If the piston does not go up, then on supplying heat, kinetic energy of the molecules will increase, pressure will increase, right? But I do not have to let the pressure to increase or decrease. I hope you're getting it. Yeah? Simple. So on supplying the heat, temperature of the gas will eventually increase, right? And on increasing the temperature, kinetic energy of the molecules should increase, pressure should increase, but we are not supposed to let the pressure of the gas to increase. So what is happening? On supplying heat, on increasing the temperature, the piston goes up, the molecules go far. The pressure which was supposed to increase due to more collisions, now the piston is going up, the molecules are again going far, due to which entire process is nullified, right? One way we are trying to increase the pressure, but another way the piston is going upwards, right? Another way there is decrease in the pressure happening. So eventually it nullifies basically. So the pressure remains constant only. It does not change. Okay. So on increasing the temperature, piston goes up, volume of the container increases, and hence volume of the gas increases, right? So that's what we said. On increasing the temperature of the gas, volume of the gas will increase, right? I hope it's clear to everyone. If it's clear, let me know once in the chats quickly. Let me know once in the chats if it is clear. If you got to know why it happens. Quickly. Yes or no? Yes or no, people in the chats. Quickly. Quickly, people, with the thumbs ups, everyone. Perfect. Now, guys, since you got it, right? Now there is this particular relation which we have. In Boyle's law, we got one relation, P multiplied by V is constant, right? The product of pressure and volume does not change at all in Boyle's law. Here V divided by T is constant. That means the division of volume and temperature. Is not going to change. Since we know on increasing the temperature, volume will increase, right? On increasing the temperature, volume will increase. On increasing the temperature, volume will increase. But nothing happens to the division of volume and temperature. What does that mean? That means if you increase the temperature by 2 units, volume also gets increased by 2 units, and 2 gets cancelled out, and V by T remains constant only. It does not change, right? It does not change at all. So do remember from now onwards, the division of volume and temperature, as far as the Charles law is concerned, it remains constant for a particular gas which is there in the container. And eventually, you get this particular relation, which is only valid when number of moles and pressure of the gas is kept constant. Perfect. Now, what is important here? Important here are questions, right? But before solving the questions, we are going to have a look on the graphs which are related to Charles law. Let's have a look on the graphs which are related to Charles law. Graphs related to the Charles law. Okay. My dear students, the first graph which we are going to plot here, that's going to be between volume of the gas and temperature of the gas in Kelvin. The first graph which we are going to plot. The second one, volume of the gas versus temperature of the gas in degrees centigrade. This is the second one, for example. The third graph which we are going to plot, what is that? That's going to be volume of the gas versus 1 divided by temperature. And the temperature here is in Kelvin. Let's try to plot these three graphs right now. And after some time, we'll plot some more graphs as well. Okay. First of all, since we are going to plot the graphs related to Charles law, so I'll be using the basic equation of the Charles law. And basic equation of the Charles law says V is equal to K constant multiplied by temperature in Kelvin. Right? This is the basic equation. Now, my dear students, over here, you're plotting volume along y-axis. You're plotting temperature in Kelvin along x-axis. Temperature in Kelvin along x-axis. So in this equation, volume is being plotted along y-axis. Temperature in Kelvin is being plotted along x-axis. So this K automatically becomes your M. So y is equal to mx. It's going to be a straight line like this. Okay, number one. Number two, if you ask me about the slope, slope means M. And M over here is equal to K, right? When you compare it, M is basically K, right? And you know, K over here, as per Charles law, is equal to NR divided by P, right? This is the slope of the graph. I hope it's clear. I hope all this is clear to you, yeah? In the similar way, people, let's have a look on one more graph. Volume you're plotting along y-axis. Temperature in degree centigrade, you are plotting along x-axis. Unacademy NEET English is asking you guys, are you guys getting it? Yeah, guys, show some josh to them, yeah? All right. So you're plotting volume along y-axis, you're plotting temperature in degree centigrade along x-axis. Now, again, the graph is related to the Charles law. The graph is related to the Charles law. Okay, so I'll be again using the basic equation as per the Charles law is concerned. Charles law says volume is equal to K multiplied by temperature in Kelvin. But my dear students, I'm going to plot temperature in degree centigrade along x-axis. But in this equation, we have got temperature in Kelvin here. It's not in degree centigrade. So it's time to convert it, right? It's time to convert it. So you can write it like this. V is equal to K. Temperature in Kelvin, you can write it as temperature in degree centigrade plus 273.15, right? So you can say V is equal to K multiplied by temperature in degree centigrade plus 273 K. Yeah? Now look at this particular equation. Well, my dear students, if you look at this particular equation, this V over here, this volume over here, you're plotting along y-axis. So instead of V, I'm writing Y. Temperature in degree centigrade is plotted along x-axis. This K automatically becomes your M, and this whole term becomes your C. In the middle, you have got plus. Y is equal to mx plus C. Y is equal to mx plus C. It's going to be a straight line like this. Yeah. At the same time, if I ask you about the slope of the curve, if I ask you about the slope, slope is basically M. And when you compare the two equations, M over here is equal to K, and K is nothing, that's NR divided by P. Right? If you ask me about the intercept, the distance from the origin to the point from where the graph starts, intercept, which is C, and C value over here is basically equal to 273K. So it's 273K. K is nothing, that's NR by P. Okay? Perfectly done. Now, at the same time, one more graph which we have to plot. Volume we are plotting along y-axis, and 1 by T we are plotting along x-axis. Yeah? 1 by T we are plotting along x-axis. Now, my dear students, the basic equation as per Charles law, V is equal to K multiplied by temperature in Kelvin. My dear students, can I write the same equation in a different format? Can I say V is equal to K divided by 1 by T? Will it make a difference? What do you think? Will it make a difference? K divided by 1 by T. T again comes up. It becomes V is equal to KT. No difference at all. Yeah. So this particular volume term, you are plotting along y-axis. So instead of V, you are going to write Y is equal to K divided by. Instead of 1 by T, you are going to write X. And whenever you need to plot a graph between two variables which are inversely proportional to each other, the nature of the graph is rectangular hyperbola. Right? And my dear students, one thing which we skipped, what was that? Since we are making all the graphs related to Charles' law, and when it comes to Charles' law, pressure of the gas is kept constant. So P is constant here. In all the graphs, I'm keeping the pressure constant. Okay? Right? Perfect. And over here, this particular graph which we got, in which pressure is kept constant, this particular graph, you can call it as isobar as well. You can call it as isobar as well. No issues at all. So how many graphs we made till now? 3. Now there are 2 more. Let's see what kind of other graphs we can draw as far as the Charles law is concerned. We can draw the graph between V by T versus T. We can plot a graph between V by T versus V. We can plot a graph between Vt versus T square. We can plot a graph between Vt versus T. Vt versus T. And there are a few more graphs which you can plot. But let's try to form all these first. Few minutes back I told you, as per Charles' law is concerned, on increasing or decreasing the temperature, what happens to the division of volume and temperature? Nothing remains unchanged, right? Similarly, on increasing the volume or decreasing the volume, what happens to the division of volume and temperature? Nothing remains unchanged, right? But the students at the same time, now it's Vt versus T square. Vt you are plotting along y-axis. T square you are plotting along x-axis. Now the basic equation says that V is equal to K multiplied by T. But my dear students, along y-axis we are not plotting volume. Along y-axis we are plotting Vt. So I'll be multiplying this equation throughout by temperature so that it becomes Vt is equal to Kt square. I multiplied the equation throughout by temperature. Why? Because I did not want V here. What did I want? I wanted Vt, right? That's why I did it. Yeah? Now, this Vt over here, you're plotting along y-axis. So instead of Vt, you're writing y is equal to. Instead of T square, you're writing x. So K becomes your M. Y is equal to mx. Isn't it going to be a straight line? Simple, done and dusted, right? One more graph we have. It's going to be Vt, which you're plotting along y-axis, and temperature in Kelvin along x-axis. You know the basic equation. V is equal to K multiplied by T. This is the basic equation. Multiply throughout by temperature. It becomes Vt is equal to Kt square. Vt is equal to Kt square. This Vt you are plotting along y-axis, right? Only T you are plotting along x-axis. Only T. So only instead of T you are writing x. But this is T ka square. So x ka square. Y is equal to Kx square. Isn't going to be parabola opening upwards? Right? Simple and basic. Correct, people? So these were a few more graphs. Are there other graphs? Yes, there are other graphs as well. Let's see what kind of other graphs we can form. For example, if I ask you to plot a graph between volume of the gas versus square root of temperature in Kelvin, will you be able to do that? You should be. Number 1. Number 2. Log of V versus log of T. This is one more graph. This is one more graph, for example. Yeah? Now, people, since volume you are plotting along y-axis and root of temperature you are plotting along x-axis. Correct? The basic equation says V is equal to K multiplied by T. But my dear students, are we plotting temperature along y-axis? No. We are plotting square root of temperature along y-axis. So this equation I'll be converting in a different format. I'll say V is equal to K. Instead of T, I'm writing square root of T ka square. Will it make a difference? No. Square and root eventually gets cancelled. Again, we get the same equation. V is equal to KT. Now, this volume we are plotting along y-axis, square root of temperature, root of T. You are plotting along x-axis, but this is root of T ka square here. So y is equal to kx square. It has to be parabola opening upwards, right? Simple. Correct? Yeah? Perfectly done. Similarly, this is log of v, which you are plotting along y-axis. This is log of t, which you are plotting along x-axis. The basic equation says v is equal to k multiplied by t. This is our basic equation. V is equal to k multiplied by t. My dear students, we do not want v over here. What do we want? We want a log of v. So I'll be multiplying this equation throughout by log. So it becomes log of v is equal to log of k multiplied by t. I multiplied both sides by log. Now, if you ask, log of v is equal, log of m into n becomes log of m plus log of n. Will it make a difference? No, just the property of log. Okay. So before this log t, what do we have? There is nothing. Nothing means there is 1, right? Log v, you are plotting along y-axis. Log t, you are plotting along x-axis. This 1 over here, it's m basically. This log k over here is c. And in between, you have got sign positive. Y is equal to mx plus c. Y is equal to mx plus c. It's going to be a straight line like this. If I ask you about the slope, slope is basically tan of theta. Slope is basically m. Slope is basically m, right? And what is the m value which you can see over here? M value over here is 1. And if m is 1, that means tan of theta is equal to 1. Tan theta 1 means theta has to be 45 degree. And what is theta exactly? Theta is the angle which the graph makes with the positive x-axis in the anti-clockwise direction. So this is 45. Yeah. And at the same time, people, if I ask you what about the intercept, the distance from the origin to the point from where the graph starts, the c value I'm asking you, c is nothing, it's log of k. C is basically log of k. Correct? These were some very important graphs which you are not going to mug up. You are going to understand like how they are made. Okay? I hope it's super clear to you. Now, people, I can ask you a question here, which you should be able to solve at least. I can ask you a question, a graphical question over here. Okay? I'm plotting few graphs between volume and temperature in Kelvin. Okay? The graphs are like this. Straight lines, first straight line, second straight line, third straight line. This was made at pressure P1, this was made at pressure P2, this was made at pressure P3. I'm asking you, which pressure is more? Is P3 more than P2 more than P1? Or P1 more than P2 more than P3? What do you guys think? You should be able to answer this because I've already told you how to solve these sort of questions. What is the thing which you'll be doing? What is something which you'll be doing? You'll be first of all drawing a straight line. After drawing a straight line parallel to y-axis, mark these points. After marking these points, get the corresponding y-axis value. Your y-axis is nothing, that's volume. Corresponding to pressure P1, the volume here will be V1. Corresponding to pressure P2, volume here will be V2. Corresponding to pressure P3, volume here will be V3. Now this is V1, this is V2, and this is V3. So look at all these things. I'll say V3 is maximum followed by V2 followed by V1, right? V3 is maximum followed by V2 followed by V1. Now dear students, use the ideal gas equation again. What is ideal gas equation all about? P is equal to nRT divided by V. Correct? Since you have drawn a straight line parallel to y-axis, that means you are keeping the x parameter constant. What is x parameter here? It's temperature. So basically, you are keeping temperature constant. R is already constant. Moles are already constant. So can I say pressure is inversely proportional to volume? Yes, pressure is inversely proportional to volume here. So more the volume, lesser the pressure. More the volume, lesser the pressure. More the volume, V3, more. Lesser has to be the pressure. So P3 has to be less than P2, which has to be less than P1. So this has to be the relation between P1, P2, and P3. I hope it's clear. Quickly in the chats. Quickly let me know in the chats if it's clear to everyone. Perfect. All right. So people, this was the first statement of the Charles law. But the Charles law is not over yet. There is one more statement. There is one more statement of the Charles law. Let's have a look what that statement is. Statement second. Statement second. Let's see what the statement says. The statement is like this. For a fixed amount of gas, for a fixed amount of gas at constant pressure, at constant pressure, at constant pressure, volume increases or decreases by 1/273 of its volume at 0 degree centigrade. For every 1 degree, rise or fall in temperature. For every 1 degree rise or fall in temperature. Now let's have a look what this statement exactly means. Understand. My dear students, imagine that this is the container over here, right? This is the piston which is fitted at the top. These are the ideal gas molecules present in the container. The container is, for example, closed on all the sides. There is no leakage at all, right? Yeah. I said Green Park. What is Green Park, Bala? Okay, so this is a closed container basically. The container is closed on all the sides. So what does that mean? That means number of moles of gas I'm keeping constant. Number one. At the same time, if I have to apply Charles' law to this particular gas, I'm not supposed to let the pressure of the gas to change. So I need to keep the pressure of the gas constant as well. I need to keep the pressure of the gas constant as well. Then only I can apply Charles' law to this gas. Let's assume that this particular gas over here, it's kept at temperature 0 degree centigrade. Let's say the temperature of the gas in the container. The temperature of the gas in the container is 0 degree centigrade. Let's assume when the temperature of the gas in the container is 0 degree centigrade, volume of the gas, for example, is V0. What is V0? V0 is the volume occupied by the gas when the temperature of the gas is 0 degree centigrade. Okay. Now, dear students, the Charles' law says that if you increase the temperature by 1 degree centigrade, if you increase the temperature by 1 degree, since we know volume is directly proportional to temperature in Kelvin, right? So if you increase the temperature, what will happen to volume? Volume will increase. Now, the gas is right now at 0 degree centigrade when the volume of the gas is V0. Now I'm increasing the temperature of the gas by 1 degree. If I increase the temperature of the gas by 1 degree, Charles' law says that volume of the gas will eventually increase. How much? It will increase by this much of amount. 1/273 of V0 amount. It will increase by this much of amount. I hope you're getting it. I hope you're getting it. Yeah? So dear students, this is the gas in the container. The gas is kept at 0 degree centigrade. Volume occupied by the gas is V0. Right? Now, as per the Charles' law is concerned, if you increase the temperature by 1 degree centigrade, volume of the gas will eventually increase. By how much? 1/273 of V0. Now, if I ask you one thing, have a look. If I ask you one thing, if I ask you, what is the volume of the gas at 0 degree centigrade? If I ask you, what is the volume of the gas at 0 degree centigrade? My dear students, volume of the gas at 0 degree centigrade is V0, right? Now, if I ask you, what will be the volume of the gas at 1 degree centigrade? What will be the volume of the gas at 1 degree centigrade? When the gas's temperature is 1 degree centigrade, what will be the volume occupied by the gas? Can I say, before 1 degree, the gas was at 0 degree, and at 0 degree, volume was V0. Now you have increased the temperature by 1 degree. And when you increase the temperature by 1 degree, this much amount of volume is increased. So can I say, this is the new volume of the gas when the gas is kept at 1 degree, right? If I ask you, what will be the volume of the gas at 2 degrees centigrade? It will be, before 2 degree, the gas was at 1 degree. And at 1 degree, this was the volume. Now you are going from 1 degree to 2 degree. That means you are increasing the volume of the gas by this much of amount again. So it becomes V naught plus 2 times V naught by 273. This is now the new volume of the gas when the gas is at 2 degree. Correct? And my dear students, you need not to remember all this. I'm just going to give you one result which you are going to use directly from now onwards. So do remember, volume of the gas at temperature T degrees centigrade. Volume of the gas at temperature T degrees centigrade is equal to V naught plus V naught divided by 273 multiplied by T degrees centigrade. Now see whether this equation is applicable to it or not. But remember, right here in this equation, you are using the temperature in degrees centigrade. Okay? So dear students, if the temperature of the gas is 0 degree, temperature 0 degree, this whole term becomes 0. So volume of the gas at 0 degree becomes V naught, which is absolutely correct. Volume of the gas at 0 degree is V naught. Correct? Now, what do? If the temperature of the gas right here is 1 degree, keep the T value as 1. So its volume of the gas at 1 degree becomes V naught plus V naught by 2. When you keep the temperature of the gas 2 degree here, right? Keep the T value 2, V naught plus 2 times V naught by 27. When you keep the temperature of the gas as minus 1 degree, keep the T value minus 1, it becomes V naught minus V naught by 270. Okay? Perfect. Now, my dear students, if you keep the temperature of the gas as minus 273 degrees centigrade, if you keep the temperature of the gas as minus 273 degrees centigrade, what's going to happen? I'll say volume of the gas at minus 273 degrees centigrade will be equal to V naught. It's going to be plus V naught divided by 273 multiplied by minus 273. 273 cancel. V naught minus V naught comes out to be 0. V naught minus V naught comes out to be 0. And let me tell you, that temperature at which volume of the gas becomes 0, we call that particular temperature as absolute 0, right? So let me write its definition first. I'm writing it like this. That temperature at which gas ceases to exist is termed as absolute 0. And which temperature that is? That is minus 273 degrees centigrade. I hope it's clear to you. Right? Perfect? Perfect, people? Now one more thing. Since we know, as far as the Charles law is concerned, when you increase the temperature of the gas, its volume will increase. When you decrease the temperature of the gas, volume will decrease. Right? Volume will decrease. Now imagine that the gas was at 0 degree when the volume of the gas was V naught. Now you are decreasing the temperature of the gas. When you will decrease the temperature of the gas, what will happen to the volume of the gas? You tell me. Volume of the gas will decrease. And how volume of the gas will decrease? The piston will slowly keep on coming down. While decreasing the temperature, the piston will keep on coming down. And if the piston is coming down, by decreasing the temperature, the piston is coming down. That means the gas molecules are coming closer. If the gas molecules start to come closer, can I say the gas is tending towards liquid state? Right? And further on decreasing the temperature, that liquid can tend into solid. Perfect. So do remember, before reaching minus 273 degrees centigrade, the gas loses its identity. There will be no gas present in the container. It would have lost its identity. Okay? So that's why we say that particular temperature at which the gas ceases to exist. You cannot find a gas at that temperature. That temperature is what we call as absolute. Right? Because the gas ceases to exist. You cannot find it. The gas would have already lost its identity, lost its originality before attaining that temperature. Okay? Now one more thing. Few minutes back, if you remember, we have drawn one graph. And the graph was between volume of the gas versus temperature of the gas in degrees centigrade, right? This was the graph. If you remember, this graph started from here and it was a straight line like this. It was a straight line like this, right? Perfect. This particular point represents 0 degree. And at 0 degree, volume of the gas is V0. We know it. At 0 degree, volume of the gas is V0. Now, my dear students, if you extend this particular line over here, it's going to cut here. It's going to cut here. If I ask you, what are the coordinates of this particular point? The coordinates of this particular point. X coordinate is, what is Y coordinate here? Y coordinate is 0. Y coordinate is 0. What is X coordinate here? X coordinate will be minus 273 degrees centigrade. Right? Minus 273 degrees centigrade. So these are its coordinates. Perfect. This is your X coordinate, which is temperature. This is your Y coordinate, which is volume. Right? And at minus 273 degrees centigrade, volume of the gas becomes 0. And this particular point, it represents what? It represents your absolute 0 here. It represents your absolute 0. I hope you guys are clear with all this again. Yeah? Done? So this was your what? This was your Charles' law. Now moving on to the third law. What is that third law? That's what you call as Gay-Lussac's law. That's what you call as Gay-Lussac's law. The way we define the Charles' law, the way we define the Boyle's law, in the similar way, you guys are going to define the Gay-Lussac's law. And it's simple again. For a fixed amount of gas, for a fixed amount of gas at constant volume, pressure of the gas is directly proportional to temperature of the gas in Kelvin. Temperature of the gas in Kelvin. So first of all, let me write its mathematical statement, then I'll make you understand what it means. So as far as this particular law is concerned, pressure of the gas is directly proportional to temperature of the gas in Kelvin. And this particular statement is only valid when number of moles and volume of the gas is kept constant. Dear students, if I remove the proportionality sign, it has to be constant multiplied by temperature in Kelvin. So this is the first equation which I would want you guys to remember. Now this K over here is something which I call as Gay-Lussac's constant. And what about its value? Its value has to be equal to nR divided by V. Like we have Charles' law. In the Charles' law, the Charles' constant value is nR by P. Here it's nR by V. You can check it out too. And you know the procedure, right? You just have to compare this equation with the ideal gas equation. You'll be getting the value of K. Yeah? Perfect. Now similarly, I can write it like this. P divided by T is equal to constant. This is one more equation which has got significance. And similarly, from this particular equation, you can get one more. P1 divided by T1 is equal to P2 divided by T2. This is one more equation which we can use in the equations, and it's only valid when number of moles and volume of the gas is kept constant. Now this is the simplest law among all. This is the simplest law, right? There is nothing to, I must say, there is nothing to think here basically. Imagine that this is the container. The container is closed on all the sides. The piston which I've used over here, it's non-movable piston. The piston cannot move. If the piston cannot move, that means volume of the container is not going to change. And if the volume of the container is not going to change, that means volume of the gas is not going to change. That's how I'm keeping the volume of the gas constant, right? Similarly, the container is closed on all the sides. That means number of moles of the gas is kept constant as well. First thing which you need to know, Gay-Lussac's law is not applicable to a gas under all conditions. No, it's applicable to a gas only when number of moles and volume of the gas is kept constant, right? It's applicable then only, otherwise it's not. Okay, now, since the moles and volume of the gas is kept constant, so it has to follow what? It has to follow the Charles' law. Sorry, it has to follow the Gay-Lussac's law. And what Gay-Lussac's law says? Pressure of the gas is directly proportional to temperature of the gas in Kelvin. That means if you increase the temperature of the gas, the pressure of the gas will automatically increase. If you increase the temperature of the gas, how would you increase the temperature of the gas first of all? How will you increase the temperature? By supplying heat. When you supply heat to the gas, what is going to happen to the kinetic energy of the molecules? Kinetic energy of molecules will increase, number of collisions will increase, and eventually pressure will increase. So on increasing the temperature of the gas, the pressure of the gas will increase. Okay? The pressure of the gas will increase. Similarly, on decreasing the temperature, pressure will decrease. I hope that's clear, right? It's evident. At the same time, this particular equation has got significance. Since you know that on increasing the temperature, what happens to pressure? Pressure also increases. But division of pressure and temperature will always remain constant. On increasing the temperature, no doubt pressure will increase. But P divided by T value will remain as such. It's not going to change. So if temperature is increased by a factor 2, automatically pressure will be also increased by a factor 2. And 2 gets cancelled. Nothing is going to happen to the P divided by T value. So do remember the division of pressure and volume. The division of pressure and temperature, sorry. As far as Gay-Lussac's law is concerned, the division of pressure and temperature, it remains constant. As per Boyle's law, the product of pressure and volume. As per Charles' law, the division of volume and temperature. And here, the division of pressure and temperature. It remains constant. I hope it's clear. Now, people, there are some graphs which I'm damn sure you can easily form now. I'm not going to teach these graphs in detail now because you know them already, right? Because we have discussed all these graphs. So the first graph is pressure versus temperature in Kelvin. Keep on writing in the chats what is the nature of the curve. Keep on writing in the chats what will be the nature of the curve. Pressure of the gas versus temperature of the gas in degrees centigrade. Pressure of the gas versus 1 divided by temperature. P divided by T versus T. Sorry, it's not 1 by, yeah, it's 1 by temperature. P by T versus T over here. Similarly, few more graphs. You should be able to make these graphs easily now. P by T versus T. Then you have got PT versus T square. Then you have got PT versus T. Then you have got P versus root T, right? And at the end, I'm making log P versus log T. Well, we can make one exponential graph as well, but leave that aside. Okay, all these graphs we have formed. In the Charles law, there is only one difference. Wherever you are seeing P, it used to be V, right? So just interchanged. Rest, everything is same. So P versus temperature in Kelvin, it has to be a straight line, right? And its slope is going to be nR divided by V here, not nR by P. Pressure versus temperature in degrees centigrade, it's going to be like this. P versus 1 by T, it's going to be hyperbola. P by T versus T, it's going to be a straight line. All the graphs are same, right? All the graphs are same, whatever we have discussed. Straight line. Straight line. Parabola. Parabola. Like this. All the things are same, no change at all, right? All the things are same, no change at all. Is everything clear? If all these graphs are clear to you, let me first of all tell you, we made all these graphs when volume of the gas was kept constant, and these graphs are what we call as isochores. So these are what you call as isochores over here, where volume of the gas is kept constant. I hope it's again clear. Right? I hope it's clear. Now people, if I give you a question, you guys are going to answer this now. Now you guys are going to answer this question. For example, I'm making a graph between pressure and temperature in Kelvin, right? These are some straight lines which I got. V1, V2, and V3. Now tell me, which volume is more? V1, V2, or V3? What do you think? Quickly. Quickly, people. Which volume is more? Quickly. The same procedure will be using again. We are not going to do some new procedure. Mark a straight line. Mark these points. Get the corresponding y-axis value. This has to be P1. This has to be P2. This has to be P3. So I can say P3 is greater than P2, which is greater than P1. Use the ideal gas equation. P is equal to nRT divided by V. The straight line which we have drawn, that means we are keeping the x parameter constant. X parameter is temperature. Temperature is constant. These terms are also constant. So pressure is inversely proportional to volume. So more the volume, lesser the pressure, right? Or more the pressure, lesser the volume. More the pressure, lesser the volume. So V3 has to be less than V2, which has to be less than V1. Correct? The same procedure which I have been teaching you from past 2 hours, right? Nothing different. Nothing different, guys. Is it clear? Perfectly done? Perfectly done? Now the statement number 2. Statement number 2 for this Charles law. Okay, one homework question I'm going to give you. Do let me know its answer in the comment section at the end of the session, okay? Comment section. Do not try it now. Comment section. I'm giving you one more question like this. It's pressure versus square root of temperature. Pressure versus square root of temperature. This one graph, one more graph, and one more graph. V1, V2, and V3. Do tell me the relation about this V1, V2, and V3 afterwards, not now. Okay, afterwards. V1, V2, and V3. All right, people. Statement second of the Gay-Lussac law. Statement number 2. Statement number 2 says that for a fixed amount of gas, at constant volume, pressure of the gas increases or decreases. Pressure of the gas increases or decreases by 1/273 of its pressure at 0 degree centigrade for every 1 degree rise or fall in temperature. For every 1 degree rise or fall in temperature. What does it mean? Again, we are going to explain it in the similar manner. Imagine that this is the container. Imagine that these are the gas molecules in the container. Let's imagine that the gas is right now at 0 degree centigrade. For example, when the gas is kept at 0 degree centigrade, the pressure of the gas is P0. The pressure of the gas is P0. Now, a few minutes back, we saw pressure of the gas is directly proportional to temperature. Now, if you increase the temperature of this gas, what will happen to its pressure? Pressure will increase. If you increase the temperature, pressure will increase, right? Perfect? Yeah? If you increase the temperature, pressure will increase. Now, Gay-Lussac law says that when you increase the temperature by 1 degree, pressure increases by a factor of 1/273 of P0. This much will be the increase in the pressure on increasing the temperature by 1 degree, right? So, if the pressure of the gas at 0 degree was P0, so if I ask you, what will be the pressure of the gas at 1 degree? It will be P0 plus P0 by 273, right? Pressure of the gas at 2 degree, P0 plus 2 times P0 by 273. But we are not going to do that. We are going to remember one particular equation, that's all. I'll say pressure of the gas at any temperature T degree centigrade is equal to P0 plus P0 divided by 273 multiplied by T degrees centigrade. So this is the equation which we guys are going to remember in order to calculate pressure of the gas at any temperature in degrees centigrade. In this equation, we are using temperature directly in degrees centigrade, okay? I hope it's again clear to everyone. Yeah? Done? Done? If the gas is at 0 degree, put the value of T as 0. This term becomes 0. So pressure of the gas at 0 degree is equal to P naught. If the temperature of the gas is 1 degree, right? So it's going to be P naught plus P naught by 273. 2 degree, P naught plus 2 times P naught by 273. Minus 1 degree, P naught minus P naught by 273. You just have to put the value of temperature, nothing else. Right? So let's move on now to the fourth gas law. What is the fourth gas law? That's simplest. That's simplest among all. That's Avogadro's law. Avogadro's law. What Avogadro's law is all about? It has got two statements again. So let's have a look. At constant pressure and temperature. At constant pressure and temperature. At constant pressure and temperature. Volume of the gas is directly proportional to the temperature of the gas in Kelvin. Sorry, not to the temperature, to the moles of the gas. At constant pressure and temperature, volume of the gas is directly proportional to the moles of the gas. Let me write it in the mathematical form first. So I would say volume of the gas is directly proportional to moles, but this particular statement is only valid when pressure and temperature of the gas is kept constant. When pressure and temperature of the gas is kept constant. Okay. So my dear students, first thing, if you remove the proportionality sign, it has to be constant multiplied by n. Right? So here, you can do one more thing. V divided by n is equal to constant. This will be one more equation. So here you can use one more equation. V1 divided by N1 has to be equal to V2 divided by N2. This can be one more equation which will be used in the equations. Right? These are different equations basically which can be used in the equations. So dear students, let's try to understand what this law is all about. So first of all, have a look. Over here, this is the piston, right? I mean, this is the container. And at the top, what do we have? We have got a piston fitted at the top. And these are the gas molecules basically which are there in the container. These are the ideal gas molecules, for example, which are there in the container. Okay? Now understand. First thing, the ideal gas which is there in the container. Can I use Avogadro's law for this ideal gas? Avogadro's law is not used under all conditions. It is used only when the pressure and temperature of the gas is kept constant. It is used only when the pressure and temperature of the gas is kept constant. I'm assuming that the pressure and temperature of the gas is constant. I'm not letting the pressure and temperature of the gas to change. That's what I meant by the term pressure and temperature is constant. Now, in this gas, for this gas, we can use the Avogadro's law. And Avogadro's law says that volume is directly proportional to moles. What does that mean? That means if you increase the moles of the gas in the container, volume will automatically increase. If you decrease the moles of the gas in the container, volume will automatically decrease. Why is that? Let's have a look. My dear students, first of all, imagine that I am introducing some extra gas in the container. Imagine that I'm introducing some extra gas in the container. Imagine that. If I'm introducing some extra gas in the container, can I say I'm increasing the moles of the gas in the container? Yes, I'm increasing the moles of the gas in the container. If I'm increasing the moles of the gas in the container, can I say the number of molecules in the container will eventually increase? Yeah. And if the molecules in the container increases, they say pressure will start to increase. But do I have to let the pressure to change? I do not have to let the pressure of the gas to change. By the addition of gas, by the introduction of more moles in the container, the pressure of the gas should increase. But we are not supposed to let the pressure to increase. That's why when you try to introduce the gas in the container, at the same time, the piston slowly goes up, such that molecules again go far, right? Such that it nullifies the effect of the addition of moles to the pressure. I hope you're getting it. Yeah? So, since we are introducing moles, we are introducing extra gas in the container. So, number of moles of the gas are increasing. Molecules are increasing. Pressure will start to increase, but we do not have to let the pressure to increase. So, a piston should go up so that molecules will again go far, collisions will be less, pressure will remain the same. Right? So, due to the introduction of moles, pressure was supposed to be increased. But since the piston is at the same time going up, the pressure is decreasing simultaneously. On one side, pressure is increasing. On the other side, pressure is decreasing. So it nullifies the effect. It remains the same, right? So what happened? Basically, by the introduction of more moles in the container, the piston got up. Volume of the container increased. That means the volume of the gas increased. That's what I was telling you, right? That's what I was telling you. On increasing the moles, the volume of the gas increased, right? Yeah. On increasing the moles in the container, volume of the gas increases. I hope this is clear. Similarly, there is one more thing. See, V by N is constant. That means, what does that mean? If you change the moles or if you change the volume, nothing will happen to the division of volume and moles. The division of volume and moles will remain the same. The division of volume and moles will remain the same. Nothing will happen to it. That's how you get this particular equation. I hope this is again clear to you, right? Nowadays, students, there is one important thing which I need to tell you. But before talking about that, this K over here is a constant, right? Avogadro's constant. What about its value? See, you know, V is equal to K multiplied by N. Ideal gas equation, I can write V is equal to N RT divided by P. This is the ideal gas equation. PV is equal to NRT. When you compare these two equations, this is V, this is V, this is N, this is N. So K automatically came out to be equal to RT divided by P, right? So K over here is equal to RT divided by P. So K over here is equal to RT divided by P. I hope this again clear. K is equal to RT divided by P. Okay? Perfect. Now there is one more statement for this Avogadro's law. What is that? That's important. What is that? Equal moles of all gases. Equal moles of all gases at same pressure and temperature. Equal moles of all gases at same pressure and temperature contains equal number of, just a second, I wrote the statement in the reverse manner. Wait. Its equal volume of all gases at same pressure and temperature contains equal number of moles, hence equal number of molecules, full stop. Atoms can be the same. Atoms can be the same if atomicity of the gases is same. Let's try to understand what the statement exactly is all about, what is meant by it. See guys, imagine that you have got three identical containers. Imagine that you have got, for example, three identical containers. Okay, just to make you understand, I'm telling you that. For example, in this container, we have got O2 gas. Here we have got O3 gas. Here you have got carbon dioxide gas, right? One container contains, this container contains O2 gas. So there will be molecules of O2. Molecules of ozone will be here in this container. Molecules of carbon dioxide will be here in this container. I would say the pressure and temperature of all these three gases is same. The pressure and temperature of all these gases is same. At the same time, since the containers are identical, That means volume of all the container is same. All the containers are same, right? Whatever is the volume of this container, the same is the volume of this container, the same is the volume of this container. And we know ideal gas occupies the volume of container. And if the ideal gas occupies the volume of container, what does that mean? That means I've got equal volume of all gases. I've got equal volume of all gases. Imagine that the volume of the first container is 5 liters, right? Imagine volume of the first container is 5 liters. Second container also 5 liters. Third container also 5 liters, right? Whatever is the volume of container, same is going to be the volume of gas. So do I have the equal volume of all the 3 gases? Equal volume of all the 3 gases at same pressure and temperature. The pressure and temperature of all these 3 gases same. So equal volume of all gases at same pressure and temperature. They'll be containing equal number of moles. If the number of moles of O2 in the first container is N, that means number of moles of O3 in the second container will also be N. This will also be N. Equal volume of all gases at same pressure and temperature contains equal number of moles. Hence, equal number of molecules. Moles multiplied by Avogadro's number gives me the molecules. Moles multiplied by Avogadro's number, molecules. Moles multiplied by Avogadro's number, molecules. Are the molecules everywhere same? Yes, the molecules are also everywhere same. Yes, the molecules are also everywhere same. Now, what about the atoms? What about the atoms? Tell me one thing. One molecule of O2. Can I say one molecule of O2 contains 2 atoms? Yes, one molecule of O2 contains 2 atoms. Therefore, N Na molecules. N Na molecules of O2 will contain 2 times N Na atoms. So these many atoms are there in the first container. Similarly, in the second container, 3 times N Na atoms will be there. In the third container, again 3 times N Na atoms will be there. Now, if I ask you whether the atoms in all the 3 containers are same or different, atoms are different, right? But if you look at these 2 gases, this is O3. Its atomicity is 3. One molecule contains 3 atoms. One molecule contains 3 atoms. This is triatomic, this is triatomic. So atomicity of these 2 gases is same. And number of atoms present in both the containers is also same. So atoms can be the same if the atomicity of the gases is same. I hope this is clear to everyone. Equal volume of all gases present at same pressure and temperature contains equal number of moles. Hence, equal number of molecules. Atoms can be the same if the atomicity of the gases is same. Right? Thank you, Pranav. Thank you. Atomicity means number of atoms in one molecule. Right? It is diatomic. It is triatomic. It's triatomic. Perfect? All right. So these were your gas laws. Now, people, let's try to have a look on something interesting. Ideal gas equation. Ideal gas equation. So till now, how many laws did we discuss? We discussed 4 laws, right? We discussed 4 laws. The first law, if you remember, that was pressure is inversely proportional to volume, keeping moles and temperature constant. Second was volume is directly proportional to temperature in Kelvin, keeping pressure constant. Leave the third law aside. Fourth was volume is directly proportional to moles. So I just wrote 3 laws. The first one was your Boyle's law. Second one is your Charles' law. And this one is your Avogadro's law. This one is your Avogadro's law, right? This is something which you know. My dear students, if I combine these 3 gas laws, if I combine them, right? If I combine them, what do I get? What do I get? I'll get something like this. On combining these 3 gas laws, I'll get PV is directly proportional to NT. PV is directly proportional to NT. Now, have a look. I combine these 3 gas laws, right? Whether this particular statement, whether it contains all the gas laws, check it. since I combined only 3, I had 4 gas laws, but out of 4 gas laws, I combined only 3, right? The statement which I got, it is not going to give me only the effect of 3 gas laws. It will give me the effect of all the 4 gas laws. No doubt, I made this particular statement by combining only 3 gas laws, but this statement is going to give me the effect of all the 4 gas laws. How come? Have a look. See, the first thing, pressure is directly proportional to temperature. Which was your pressure is directly proportional to temperature, which was your Gay-Lussac's law, right? So this statement, it includes the Gay-Lussac's law, number 1. Number 2, volume is directly proportional to moles, so it includes Avogadro's law as well. Volume is directly proportional to temperature, it includes Charles' law as well. If you put volume here in the denominator, so pressure is inversely proportional to volume, it includes Boyle's law as well, right? So can I say this particular statement, it's formed by combining 3 gas laws, but it gives me the effect of all the 4 gas laws. Okay? Now, what exactly we are going to do? Understand. Understand. It's simple now. If I remove the proportionality sign here, I'll be getting a constant. So it's going to be PV is equal to, and I'm writing as such, this is R, this is T, correct? This particular equation, which you have been studying for so long now, it's something which you call as ideal gas equation. This is something which you call as ideal gas equation. So ideal gas equation is what? It is PV is equal to nRT, right? This is your ideal gas equation. So this R over here, my dear students, this R is something which you call as universal gas constant, you know it. R is what you call as universal gas constant, right? And the value of R, it depends on. The value of R depends on the units of pressure and volume. The value of R, universal gas constant, it depends on what? It depends on the units of pressure and volume. Someone is asking when the chapter will end. I have no idea when the chapter will end. When it ends, you'll get to know. Even I'll get to know. Okay? Just understand and focus on the session. Always you'll be after when the session will end. Right? You're not looking about the content, which is really wrong on your part. All right. See. My dear students, I told you this R is what you call as universal gas constant, and its value depends on the units of pressure and volume. And let me tell you, this R has got exactly 3 values, which you are going to remember. R has got exactly 3 values. This universal gas constant has got 3 values. Number 1, 8.314 joules per Kelvin per mole, right? In order to reduce the calculation in the questions. In order to reduce the calculations in the questions, instead of 8.314, you can write 25 by 3. Instead of 8.314, you can write 25 by 3. It's one of the same thing. Yeah. The second value, 0.0821 ATM liter per Kelvin per mole. And to reduce the calculation, you can write 1 by 12. One more value, 1.98, or approximately you can use 2. Calories per Kelvin per mole. These are the 3 values of universal gas constant which you have to remember, right? Yes. So my dear students, in this particular states of matter chapter, these are the 2 values of R which preferably I'll be using. Okay, I hope this is clear. Right? R has got these 3 values, right? You have to remember all the 3 values. Point number 1. Point number 2. There is one more form of this ideal gas equation. What is that form? That is density form. Density form of ideal gas equation. Density form of ideal gas equation. Now, my dear students, since we know PV is equal to nRT, which is the ideal gas equation. PV is equal to nRT, right? PV is equal to nRT. So from this particular equation, can you convert it into density form? You can do that. See, I can say PV is equal to N stands for number of moles of gas, which is given mass of gas, molar mass of gas. R, this is T. P I'm writing as such. M will come here. It's going to be W divided by V. This is R and this is T. So it will come out to be PM is equal to mass by volume is density, right? DRT. This is something which you call as density form of ideal gas equation. P stands for pressure of gas, M stands for molar mass of gas, D stands for density of gas, R is the universal gas constant, T is the temperature. And do remember, density value, density of the gas here, I'll be taking in grams per liter. Density of the gas I'll be taking in grams per liter. Okay, PM is equal to DRT. This is something which you call as density form of the ideal gas equation, right? Let me tell you, any such gas, any gas which follows the ideal gas equation under all conditions, what do you call that particular gas? You call that as ideal gas, right? And what is the actual meaning of ideal gas? You'll get to know in some time, not now. Okay? Yes? Perfect. I hope this is clear to everyone. Now guys, till now I did not show you any question. I did not show you any problem, right? Now it's time to do some problems. But before doing problems, there is one thing which will help us out in order to solve the problems. What is that? That's combined gas equation. Combined gas equation will exactly help us out to solve the equations in lesser time. Okay, and what is this combined gas equation all about? Let's have a look now. Understand what I'm going to say. Imagine that you have got a container, and this particular container, it contains an ideal gas. It contains an ideal gas, okay? So these are basically the ideal gas molecules present in the container. Let's say the pressure of this ideal gas is P1, volume is V1, moles of the gas in the container is N1, and temperature of the gas is T1, right? My dear students, since this is the ideal gas, right? So if it is the ideal gas, it has to follow the ideal gas equation. And if I use ideal gas equation for the gas right now, I'll be using it like this. P1 V1 is equal to N1 R T1, right? When the gas was present at its initial state, these were its parameters, and this is how you wrote the ideal gas equation. Now people, what I'm exactly going to do? I'm going to change the parameters of this ideal gas. The pressure was P1 initially. Let me change the pressure of this ideal gas from P1 to P2. Let me change the volume of the ideal gas from V1 to V2. Moles from N1 to N2. Temperature from T1 to T2. So can I say I changed the state parameters of the gas? This P, V, and T, these are called as state parameters, right? These are called as state parameters. So basically, I changed the state parameters of the gas. And do remember, when state parameters of gas, when they get changed, the state of the gas gets changed. If the gas initially was at initial state, now the gas will be at final state. Just tell me one thing. Did I change the gas? I did not change the gas. I just changed the parameters. The gas, the nature of the gas is still same. It's still the ideal gas only. It's still the ideal gas only. It is just I changed the conditions. I did not change the gas. Now, dear students, since it is the ideal gas here, if I want you guys to write ideal gas equation for this ideal gas, which is present at final state, how you're going to do that? You'll write P2 V2 is equal to N2 R T2. So how many equations did I get? I got two equations. Right? The first equation, P1 V1 is equal to N1 R T1, P2 V2 is equal to N2 R T2. If I divide these two equations, I'll be getting one equation, which is the master equation, which is the combined gas equation, which will be used to solve the equations in lesser time. The equation becomes P1 V1 divided by P2 V2 is equal to N1 T1 divided by N2 T2. This is basically the equation which you guys are going to use in the questions, right? By using this equation, you can solve the equation in lesser time. Now, you must be thinking how to use this equation. There are a few things which I would want to tell you, which will make you're solving a bit easy, right? And what are those things? Let's have a look. Dear students, do remember, if any parameter, whenever you come across a question, whenever a question is given to you, okay? Read the question first of all. After reading the question, try to understand which parameter of the gas is kept constant. Whether pressure is kept constant, moles are kept constant, temperature is kept constant. Understand carefully. And whatever parameter is kept constant in the question, remove all those terms from the equation. For example, if you find a question in which pressure and moles of the gas were kept constant, what you'll be doing? Remove all the pressure terms and moles terms. Remove all the pressure terms and moles terms from this equation. So remove P1, P2, N1, N2 from here. You'll be left with V1 divided by V2 is equal to P1 divided by T2. This is the equation which you guys will be using in that particular equation. Simple, nothing else. Simple, nothing else, right? Okay. Now, dear students, one more thing. For example, if you find a question in which volume and temperature, for example, of the gas was kept constant, what you'll be doing? Remove all the volume terms, temperature terms, V1, V2, T1, T2. Remove them up. So what you'll be left with? You'll be left with P1 divided by P2 is equal to N1 divided by N2. This is the equation which you'll be using in the questions. Right? Perfect. Similarly, so whatever parameters, for example, if you find a question in which number of moles and temperature was kept constant, number of moles and temperature was kept constant, so you have to remove this whole side. You'll be left with only P1 V1 is equal to P2 V2. This is the equation which you'll be using at that point of time. Okay, this is the equation which you'll be using at that point of time. Right? Similarly, for example, you found a question in which hypothetical question in which pressure of the gas and volume of the gas was kept constant. So remove P1, P2, V1, V2 from here, and what I'll be left with? I'll be left with N1 T1 is equal to N2 T2. This is the equation which you'll be using in the questions. So it depends on the question basically. You have to look for the parameter which is constant for a gas and remove all the terms related to that parameter from the equation. Use the final equation and kill it. Yeah. Now it's the time to solve some questions so that you can understand each and everything properly. Okay. Just a second. The first question on the screen, quickly. You guys are going to tell me. What should be the answer of this question? What should be the answer of this particular question, everyone? Check it out. So basically, these are few graphs which are given to us, right? So you know PM is equal to DRT, right? PM is equal to DRT. Which of the following graphs is not correct? Is incorrect, they are saying. Is incorrect, they are saying. Okay, if I write it like this, PM divided by RT is equal to D. It's correct, absolutely. So density and temperature, they are inversely proportional to each other. If you want to plot a graph between density and temperature, it has to be hyperbola, but it's a straight line. So this is the incorrect one. This is something which you were supposed to choose, right? So it's question number, it's option 2. NEET 2022 question this is. Let's see what the question is. A 10-liter flask. We have got a flask, we have got a container, right? Let's assume this is the container whose volume is 10 liters. It contains 64 grams of oxygen. So it contains oxygen gas, right? Volume of the flask is 10 liter. That means the volume of the gas in it is 10 liter as well. What is the mass of gas in the container? What is the mass of gas in the container? Mass of oxygen gas in the container is 64 grams. It is 64 grams. So can you let me know how many moles of O2 are there in the container? Given mass of O2 divided by molar mass of O2. So basically, in short, you have 2 moles of O2 in the container. The oxygen gas is kept at 27 degrees centigrade. So temperature of O2 is equal to 27 degrees centigrade. That means 300 Kelvin. Okay. What are we supposed to calculate? We are supposed to calculate the pressure of O2 gas in the container. We have to assume the O2 gas to be ideal in nature. If we assume the O2 gas to be ideal, then it has to follow the ideal gas equation. So you'll say pressure of O2, volume of O2 is equal to number of moles of O2, this is R, and this temperature of O2. Simple. Now pressure of O2, we need to calculate. Volume of O2 is 10 liters is equal to number of moles of O2 to R value. Now which value of R you guys are going to use here? Which value of R you guys are going to use here? 0.0821. So 1 by 12, right? Temperature of O2, that's 300 Kelvin. One equation, one unknown. So you can easily calculate pressure of O2 and its units are going to be in atm. Right? One equation, one unknown. That's it. Yeah? Perfect. So after solving the equation, you'll be getting the final answer as 4.9 bar. Number 1. First type of question, which was basic. Let's have a look on the second type of the question. Okay. Ammonia is present in a storage tank. Let's assume this is one storage tank. Storage tank is basically a container like this. Okay. So ammonia is present in a storage tank. Let me first of all tell you, ammonia is present in a storage tank. Storage tank, the tank can withstand maximum pressure of this much. If the tank is slowly heated, at what temperature the tank will burst? Is it mentioned anywhere that there is some leakage in the tank? It's not mentioned anywhere. There is no leakage in the tank. If there would have been some leakage, it should have been mentioned here, right? But there is nothing mentioned like that. So what does that mean? If there is no leakage, that means number of moles of the gas we are keeping constant, right? My dear students, storage tank does not contain any piston as well. It does not contain any piston as well. So if there is no piston in the storage tank, volume of the tank is not going to change. So volume of the gas is not going to change. That means volume of the gas is also kept constant. So first of all, I identified two things. Number of moles and volume of the gas has been kept constant. Now, since there is ammonia gas in the container, the pressure of the ammonia gas inside the container is 2 atm when the temperature of the gas is 300 Kelvin. Okay. Now guys, understand one thing. As far as ideal gas equation is concerned, PV is equal to nRT, right? PV is equal to nRT. Now as far as the equation, volume and moles are constant. So can I say pressure is directly proportional to temperature? So this particular gas, whose moles and volume are constant, so it's going to follow particularly this equation. If you increase its temperature, the pressure of the gas will increase. If you increase the temperature of the gas, the pressure of the gas will increase. That's what we are doing. If the tank is slowly heated, we are heating the tank slowly. When we heat the tank slowly, that means we are increasing the temperature of the gas. That means the pressure of the gas will increase, right? So upon slowly heating, the pressure of the gas is increasing and the gas can withstand a maximum of how much pressure? 6 atm when the temperature of the gas was T2. The gas can withstand maximum pressure of 6 atm. And when the pressure goes beyond 6, the tank will burst. I'm assuming when the pressure of the gas is 6 atm, the temperature of the gas at that time, for example, is T2. Now check which all parameters are constant, moles and volume. Use the combined gas equation. Combined gas equation says P1 divided by P2 is equal to P1 divided by T2. P1 is 2 atm, P2 is 6 atm, T1 is 300, and T2 we have to calculate. So from this particular equation, you can calculate the value of T2, which comes out being 900 Kelvin. I'm asking you one question. At 900 Kelvin, will the tank burst? What do you think? Will the tank burst at 900 Kelvin? 900 Kelvin is the temperature at which the pressure is 6 atm and the tank can withstand 6 atm pressure. But when the temperature goes beyond 900, the pressure will go beyond 6 atm and eventually the tank will burst. So for the tank to burst, the pressure has to be greater than 600 Kelvin, right? Yes? Dream special, what is wrong in that? Just drag the video a little back, watch it from the starting itself. Right? Why are you saying you missed it? You're watching it, right? Just drag it a little back and watch it. Perfect. Now, dear students, let's try out this particular question. Let's see what this question is all about. Understand. The question is the density of certain gaseous oxide. The density of certain gaseous oxide. So basically, we have got a container containing a gaseous oxide, whatever it is. It can be N2O5, NO, whatever gaseous oxide. We have got a gaseous oxide, right? As far as the question is concerned, the density of gaseous oxide is same as that of density of O2. This is given to us as far as the question is concerned. So we have got basically two containers, one containing gaseous oxide, one containing O2, right? The density of gaseous oxide is same as that of density of O2. Now people, as far as the question is concerned, pressure of gaseous oxide is given to us as 1.5 atm, right? Temperature of gaseous oxide is given to us as 20 degrees centigrade, means 293 Kelvin, right? Pressure of O2 is given to us as 4.5 atm, and temperature of O2 is equal to 10 degrees centigrade, that means 283 Kelvin. These are the parameters which are given to me. The density of gaseous oxide, which is kept at this pressure, whose temperature is this much, is same as that of density of oxygen, whose pressure is 4.5 atm and temperature 283 Kelvin. What are we supposed to calculate? Molar mass of gaseous oxide. Molar mass of gaseous oxide is to be calculated. Do we know the molar mass of O2? Yes, we know the molar mass of O2. How much that is? 32 grams per. This is the molar mass of O2. Correct? Now people understand what I'm going to say. As far as the question is concerned, see, a few minutes back we saw one equation. PM is equal to dRT, right? So I'll say density is equal to PM divided by RT. Okay? Instead of density of gaseous oxide, can you write pressure of gaseous oxide, molar mass of gaseous oxide divided by R, temperature of gaseous oxide, is equal to density of oxygen will be equal to pressure of O2, molar mass of O2 divided by R, and this is temperature of O2. Correct? Now put the values, get the answer. So first of all, this R and R got cancelled out. And after that, pressure of gaseous oxide is given to me as 1.5. Molar mass of gaseous oxide you need to calculate, divided by temperature of gaseous oxide is 293 Kelvin, is equal to pressure of O2 is 4.5 atm. Molar mass of O2 is 32 grams per mole, divided by temperature of O2 is 283. Right? So when you cross multiply and stuff, you'll be getting the molar mass of gaseous oxide exactly as 99.3. And what are the units of molar mass? Grams per mole. So this is the molar mass of gaseous oxide which we were supposed to calculate. Right? Perfect? I'm sure it's clear to everyone. Let's try to solve a few more. Okay, let's have a look on this question. What is the question all about? A 10-liter cylinder of oxygen at 4 atm and 17 degrees centigrade developed a leak. When the leak was repaired, 2.5 atm of oxygen remained in the cylinder, still at 17 degrees centigrade. How many moles of the gas escaped? See what the question is. As far as the question is concerned, for example, we have got a container. Let's say this is the container. Okay. The volume of the container is 10 liters. And this container contains what? It contains O2 gas. So there is O2 gas in the container. Volume of the container is 10 liters. That means volume of O2 here is, which I'm representing with V1, that's 10 liters. Right? That's 10 liters. Volume of the gas is 10 liters. Right? These are the gas molecules. Now, dear students, pressure of the gas, which I'm representing with P1, it's 4 atm. Temperature of the gas is equal to 17 degrees centigrade. That means 290 Kelvin. Right? Now, as far as the question is concerned, since the gas was there in the container and these were its parameters, let's assume there were N1 moles of gas present in the container. Now, as far as the question, the tank the cylinder, it developed a leakage. It developed a leakage. For example, suddenly a hole got created here. Suddenly a small hole got created. And due to the presence of hole, what would have happened? Can I say, due to the presence of hole, some gas would have come out? But when the hole was, there was a presence of hole after some time, right? But it was fixed right after that only. There was a gas in the container. And suddenly it was observed that the tank got a leakage basically. There was a hole here. But it was fixed quickly. It was fixed quickly. So not much of the gas came out. No doubt, some of the gas came out. Some of the gas came out. But the hole was fixed quickly. It was fixed quickly. So what would have happened? So initially, if there were N1 moles of the gas in the container, finally, after the leak was repaired, will there be same amount of gas in the container? No. The gas left in the container now will be less. Let's assume the number of moles of gas left in the container now is N2. Okay, these are the number of moles left in the container because some of the gas has left, right? Okay, and after that, the leakage was repaired. Now, my dear students, the remaining moles of the gas are kept at the pressure 2.5 atm. So pressure of the gas right now, which is left in the container, is 2.5 atm. 2.5 atm, still at 17 degrees centigrade. So temperature of the gas right now is also 17 degrees centigrade, right? Initially it was 17, now also it's 17. Now also it's 17, right? If I ask you whether the volume of the container is changing or not, the volume of the container is also not changing, right? The container is the same. Therefore, volume of container does not change. And we know gas occupies the volume of container. So I must say, initially, N1 moles of the gas would have occupied 10 liters of volume. Now, N2 moles of the gas would have occupied 10 liters of volume. Nothing else, right? What would have been the difference? Here the moles in the container were more. Now the moles in the container are less. The only difference is the molecules here will be comparatively far from each other as that of before. Yeah. Initially there were N1 moles. Now finally how many moles of gas are left? N2. What do we need to calculate? We need to calculate moles of the gas escaped. How many moles of the gas escaped? Correct? Initially I had N1 moles and finally I'm left with N2 moles. So N1 minus N2 gives me the total moles of the gas which came out of the container, right? What is N1? N1 is going to be P1 V1 divided by RT1. What is N2? It's going to be P2 V2 divided by RT2. Correct? All the parameters are given to us. Put all the parameters in this expression. Put the value of R everywhere as 1 by 12, right? Put all the parameters, solve it and get the answer. That's it. Isn't it simple? Isn't it simple, people? P1, V1, T1, P2, V2, T2, everything is given to us. You can check it out. Put all the things into the expression and get the answer. So the final value will be 0.63. So approximately 0.63 moles of the gas escaped through the hole which got created. I hope it's clear to everyone. Okay. So initially there were N1 moles, right? Due to leakage, some of the gas came out of the container. And finally there were N2 moles of the gas left in the container. So N1 minus N2 is going to give us the total moles of the gas which left from the container. I hope it's super clear. Now, let's have a look on one more question. Let's see if you can solve this or not. Give it a try. The question is, as far as the question is concerned, 1 mole of N2 gas at STP. So we have got 1 mole of N2 gas. Let's say this is the container. What does it contain? It contains N2 gas. The N2 gas is at STP. How many moles of N2 gas? We have got 1 mole of N2 gas present at STP. STP means the temperature of the gas right now is 0 degrees centigrade, which means 273 Kelvin. And the pressure of the gas right now is 1 atm. This is STP condition, correct? 1 mole of N2 gas at STP. First of all, do you know 1 mole of an ideal gas at STP occupies the volume of 22.4 liters? Do you know that? 1 mole of the gas at STP, 1 mole of ideal gas in particular at STP occupies the volume of 22.4 liters. Now, dear students, in this container, we have got 1 mole of gas, correct? We have got 1 mole of gas. Now, as far as the question is concerned, 1 mole of N2 gas at STP was put into a vessel. So basically, you have got 1 more vessel here. This is 1 more vessel. Volume of this vessel here is 27 liters. Right? Volume of this vessel is 27 liters. 1 mole of N2 which was there in the first container, I am taking 1 mole of N2 out and I am putting it in this container. Right? I have introduced the same 1 mole of N2 in the second container. So how many moles of N2 are there? There is 1 mole of N2 in this container as well. Whatever N2 was there in the first container, I've taken it out and introduced it in the second container. So initially 1 mole of N2 was occupying the volume of 22.4 liters. Now, same 1 mole of N2 is occupying the volume of 27 liters. The temperature of N2 now is 600 Kelvin. 600 Kelvin. What are we supposed to calculate? What is the pressure of the gas in the vessel? In this vessel, what is the pressure of the gas? P2 we are supposed to calculate. How you guys are going to do it? How you guys are going to do it? Do you have any idea of how you guys are going to solve it? Quickly. Do you have any idea of how you guys are going to solve it? Understand. Can you just let me know one thing? Which parameter of the gas is kept constant? Do you see moles are not changing at all? Initially, 1 mole. Now also 1 mole. Moles are not changing. Moles are constant, right? If moles are constant, I'll be using the equation P1V1 divided by P2V2. Has to be equal. Has to be equal to what? N1T1. But it's only going to be T1 divided by T2 because moles are constant. Correct? So P1 is given to us. V1 is given. V2 is given. T1 we know. T2 we know. So can't we calculate P2 from here? All the parameters are given. Put all the parameters in this equation. Get the value of P2 from here. That's all. That's all. That's something which I was supposed to calculate. P2 is the pressure of the gas in the vessel. Is it? Right? I hope, guys, it is again super clear to you. Okay? One more type of question. Let's give it a try. Let's see how this sort of a question is to be solved. A vessel open to atmosphere. We have got a vessel which is open to atmosphere. Oh, this is the open vessel concept. I have not taught you open vessel concept yet. Okay. One thing, just remember for now. I'm going to teach it later on, okay? Just remember one thing for now. This is the open vessel. This is the vessel which is open on one side. And for example, you have got gas inside it. Whenever in states of matter or even in thermodynamics, whenever you see a gas present in an open vessel, right? Do remember, you'll be taking the pressure of the gas constant. I mean, there is one concept called as open vessel concept, which I'll be teaching you in thermodynamics basically. When I'll be teaching the isobaric processes, right? There I'll be teaching you that. But right now, just remember it whenever you see an open vessel basically. The gas present in an open vessel, consider pressure to be constant. Number one. Number two, a vessel open to atmosphere is heated such that 3/5 of the air in it is expelled out. I'm assuming there are some N moles of gas in the container. There are some N moles of the gas in the container. Now I'm heating the container. When I'll heat the container, what's going to happen? Some of the gas molecules will leave from the vessel. Some of the gas molecules will leave from the vessel. And I have to heat, let's say the initial temperature of the gas. The initial temperature of the gas was 300 Kelvin. Now, as per the question, I have to heat the gas. I have to heat the gas unless 3/5 of the gas from the container comes out. Initially, there were N moles. So finally, how many moles of the gas will be left in the container? We have to heat this container until 3/5 of the gas comes out of the container. So initially, there were N moles. How many moles of the gas will have to come out? 3/5 of N moles of the gas will have to come out. So these many moles of the gas will be left in the container at the end. Right? I'm assuming the temperature of the gas right now is T2. I hope you got what I said. Initially, there were N moles of the gas. Temperature of the gas was 300 Kelvin. Now you're heating the gas up. 3/5 of the gas is coming out of the container. I'm raising the temperature from 300 to T2. Then only 3/5 of the air from the container is coming out. And when 3/5 of the air is coming out of the container, there'll be only 2/5 and these many moles of the gas will be left in the container. Hope this is clear. You tell me one thing. You tell me one thing. Initially, there were n moles of the gas. The temperature of the gas was 300 Kelvin. Now, what we are doing? We are increasing the temperature. Why we are increasing the temperature? Because we want some of the gas to come out of the container. How much gas you want to come out of the container? You want 3/5 of the gas to come out of the container. That's why we are heating it up. That's why we are heating it up. So, assuming that we have to increase the temperature of the gas from 300 till T2, then only 3/5 of the gas from the container will come out. Okay. Now, my dear students, since pressure of the gas is already constant, now tell me one thing. Is the volume of container changing? Volume of container is not changing at all. It's not changing. I would say volume of the container is not changing. What does that mean? That means the volume of the gas won't change. So volume is also constant. I would say initially n moles of the gas were occupying the whole volume of the container. And now 2/5 n moles of the gas are occupying the same whole volume of the container. Yeah? So if PV is constant, use the combined gas equation. N1 T1 has to be equal to N2 T2. Correct? N1 value is N. T1 value is 300. N2 value, how much is that? 2/5 of N. T2 you have to calculate. So N got cancelled. So T2 from here comes out to be 750 Kelvin. Right? So what is the 750 Kelvin? It means that you have to increase the temperature of the gas from 300 till 750 Kelvin. Then only 2/5 of the air, then only 3/5 of the air from the container will come out. I hope you got it. Yeah? Clear? I hope it is clear to everyone. Let's have a look on one more question. An air bubble at the bottom of the lake has the radius of 1 centimeter. If the pressure at the bottom of the lake is 27 atm and the bubble rises slowly at the surface, okay, what would be the radius of the bubble at the surface, assuming temperature to be constant? Again, a very simple question. Just understand what I'm going to do. Before solving this question, let me tell you one thing. Let me tell you one simple thing. One simple thing I'm telling you, okay? Let's say this is one air bubble. This is one balloon. Let's imagine that this is a balloon. Or let me, just a second. Yeah. Imagine that this is a balloon here. And this balloon contains gas. There is gas inside the balloon. My dear students, a very small concept I'm going to tell you. Inside the balloon, there is a gas. Outside the balloon, there is atmosphere basically. Outside the balloon, there are also gases, atmospheric gases. Inside the balloon, there is a particular gas. Outside the balloon, there is atmospheric gas. If I select this part, a very small part of this circle, of this circumference, can I say from inside, internal gas molecules are colliding it? From outside, atmospheric gas molecules are colliding it? Right? Perfect. If I select a small part over here, from inside, the internal gas molecules are colliding. From outside, the atmospheric gas is colliding. Correct? So, can I say on the circumference of the balloon, can I say two pressures are acting? One is internal pressure, one is external pressure. Or one is atmospheric pressure, you can say. Correct? Now, my dear students, one simple thing. If, for example, if internal pressure is greater than external pressure, can I say expansion of the balloon will happen? The balloon will increase its size. So expansion of balloon will happen. If internal pressure is greater than external pressure, expansion of balloon will happen, right? And at the same time, if, for example, P external is greater than P internal, if external pressure is more, that means the balloon will shrink. Compression will happen. Compression of the balloon will happen. Correct? And by chance, if P external will be equal to P internal, at that time, what will happen? Will anything happen? There'll be no expansion, no compression. Correct? Expansion, compression, nothing. This is the criteria for expansion, compression. You know it. Yeah? Yeah? Now, guys, understand one simple thing. Understand one simple thing. Now, you can check, you can see exactly how we are going to solve the question which is given to us. Let's try to solve the question which is given to us now. The question says, an air balloon is present at the bottom of the lake. Let's say this is the bottom surface of the lake. This is the top surface of the lake, right? This is the top surface of the lake. And this is, for example, the bottom surface of the lake. Let's assume that, right? Top surface, bottom surface. And here, what do we have? The lake is filled with water. This is water here. This is water here, right? This is water here. As far as the question is concerned, have a look. An air bubble is present at the bottom of the lake. The air bubble is present at the bottom of the lake. This is the air bubble which is present at the bottom of the lake. It contains air in it. It contains air in it, right? When the air bubble is present at the bottom of the lake, the radius of the air bubble is 1 centimeter. So radius of the air bubble right now is 1 centimeter. Okay? If the pressure at the bottom of the lake is 27 atm. So at the bottom pressure is 27 atm. When the air bubble is present at the bottom, the outside pressure is 27 atm. But the air bubble is present at the bottom. So what would have happened? Is the balloon right now expanding or compression? Is it showing some expansion or compression right now? No. At the bottom, it's still no expansion, no compression. If at the bottom, there is no expansion, no compression, the balloon is still. That means external pressure and internal pressure will be the same. External pressure at the bottom is 27. That means the internal pressure, which is the pressure due to gas, right now will be also what? Right now, it will be also 27 atm. Because no expansion, no compression. Yeah? Perfect. Now, as far as the question is concerned, the balloon slowly rises up. Now the balloon slowly rises up. Perfect. When the balloon will start rising up, as you go down in the water, the pressure on you increases, if you know, right? As you go down in the water, pressure increases on you. You know that. Now, people, if the balloon is coming up, that means if the balloon is coming up, outside pressure decreases. If the balloon is coming up, outside pressure decreases. External pressure decreases. If external pressure decreases, that means expansion will happen. And when the balloon will reach the top, its volume will be maximum at the top. Its volume will be maximum at the top. I hope you got it. Right? Let's assume the radius of the balloon right now is R2. I need to calculate this radius of the balloon at the top. Now, my dear students, when the balloon reaches the top, after reaching the top, again there'll be no expansion compression. That means external pressure, internal pressure again will be the same. And at the top, there will be external pressure is atmospheric pressure, which is 1 atm. So internal pressure will be also 1 atm. Right? Can I say whatever amount of gas was here in the balloon, same amount of gas will be here in the balloon as well at the top. So what does that mean? Are the moles of the gas changing? Moles of the gas are not changing at all. At the same time, as per question, temperature of the gas is kept constant as well. Temperature of the gas is kept constant as well. So moles as well as temperature is constant, right? If moles and temperature is constant, use the combined gas equation. P1, V1 has to be equal to what? It has to be equal to P2, V2. P1 value is 27 atm. V1, volume of the gas in the balloon when it is present at the bottom, it's going to be equal to 4 by 3 pi R1 cube is equal to P2. P2 is how much? 1 atm multiplied by V2, 4 by 3 pi, it's going to be R2 cube. R1 value is 1, right? So this 4 by 3 pi cancel. So you got to know R2 cube is equal to 27. So R2 is just going to be equal to 3 centimeters. And what is this R2? R2 is the radius of the balloon at the top, which we were supposed to calculate. Is it clear? Quickly, yes or no in the chats with the thumbs ups, everyone. Yes or no in the chats with the thumbs ups, everyone. Quickly, guys, everyone. Everyone, guys, everyone, quickly. Perfectly done, right? Perfectly done. Okay, let's have a look on a few more things. Let's see if we have more questions on ideal gas. No, ideal gas part is done. Let's do one thing. Let's do a question based on connected containers. There is a particular type of question which is based on connected containers. Like you would have seen those questions. Two bulbs, they are joined with the help of the narrow rod, something like that, right? Those questions I'm sure you would have seen. First of all, let's have a look at the concept. Then later on we'll solve a question. You'll understand easily what it is. So people, the scenario is like this. The scenario is like this. Let's say this is one container, or let me just make it free-handed. Let's say this is a container which is attached to one more container. Okay. In the middle, I've kept a stopcock. It is a stopcock. Here, you have got a gas in this part. And here, you have got again gas in this chamber as well. Right? Volume of the gas in this particular chamber is V1. Here it's V2. Pressure of the gas here is P1. Here it's P2. Temperature of the gas here is T1. Here it's T2. Correct? My dear students, you tell me one thing. Have I kept stopcock in the middle? Yes. The stopcock, it won't let the gases to intermix right now. Right? It won't let. I've kept the stopcock. So it won't let the gases to intermix. It won't let the gases to intermix. Now you tell me one thing. Since the pressure on the left side is P1, the pressure on the right side is P2. So does that mean there is pressure difference between the containers? There is pressure difference between these two gases? There is pressure difference. And you know, gases always move. Gases flow due to pressure difference. You know that? Right? Gases flow due to pressure difference. So does that mean if I remove the stopcock, automatically due to the pressure difference, the gases will intermix till the time the pressure on both the sides becomes equal? Yeah? So pressure P1, pressure P2, the pressure is different on both the sides, right? So there is pressure difference in both the containers. So if I remove the stopcock, what will happen? On removing the stopcock, the gases will start intermixing till the time the pressure becomes equal on both the sides. Right? And my dear students, when the pressure becomes equal on both the sides, let's assume after the intermixing is done, the pressure on left hand side is P, on right hand side also, for example, it's P. Right? Is there any pressure difference now? Pressure difference now is not there. So will there be any net movement of molecules? There won't be net movement of molecules. Yeah? Now, volume of this part of the container is V1, temperature here is T1, volume here is V2, temperature here is T2. Correct? Before the arrow, this was the case of before mixing. After the arrow, this is the case of after mixing. Can you tell me how many moles of gas did we have before mixing? There were some moles of gas here. There were some moles of gas here. So before mixing, moles of gas in this particular chamber will be equal to P1 V1 divided by RT1. In this chamber, before mixing, it was P2 V2 divided by RT2. So can I say, if I add them up, These are basically the total moles present in both the chambers before mixing, right? Total moles present in both the chambers before mixing. Dear students, did you see anywhere the gas coming out from the containers during the mixing? No. So can I say total moles of the gases before mixing, it has to be equal to total moles of the gases after mixing. Perfect, because there is no gas coming out of the container. Now, after mixing, how many moles of gas we have? Some moles here, some moles here. How many moles here in this part? It's going to be P V1 divided by RT1 plus in this chamber, it's going to be P V2 divided by RT2. Perfect. So these are the total moles of the gas present in both the chambers after mixing. And we know number of moles of gas before mixing has to be equal to number of moles of gas after mixing. So my dear students, my point is that you should be able to make this sort of an equation. If you are able to make this sort of an equation, then all the questions of the connected containers you can easily solve in no time. Right? Let me show you one of the questions. Well, I have not written the question in the slides. Well, I will have to write it. Just a second. There was one question which was asked in JEE mains long back. Right? But it's a proper NEET standard question and you should be able to solve that now. The question is like this. Just a second. The question is like this. Question is two closed containers. Two closed containers of equal volume. Two closed containers of equal volume containing an ideal gas. Containing an ideal gas. Containing an ideal gas at pressure Pi. At pressure Pi and temperature Ti. And temperature Ti are connected through a narrow tube. Are connected through a narrow tube of negligible volume. If the temperature of one of the container is raised to T2, what is the final pressure? What is the final pressure? Can you give it a try? Can you give it a try, people? This is one question which was asked long back in mains, and it's a proper NEET standard question only. You should be able to solve this. What do you think? Can you? Let's see what the question is first of all. See guys. Two closed containers of equal volume. So we have got two closed containers which are of equal volume. All right. So these are, for example, two closed containers which are of equal volume, right? Let's say of equal volume containing an ideal gas. Volume of this container is, for example, V. Volume of this container is V. And these containers, what do? They contain ideal gas at pressure Pi and temperature Ti. Pressure here is Pi, temperature here is Ti. Pressure here is Pi, temperature here is Ti. Perfect. Perfectly fine. So first of all, temperature on both the sides is same as well as pressure on both the sides is same. If pressure on both the sides is same, that means there is no pressure difference. If there is no pressure difference, there'll be no net moment of gas. There'll be no net moment of gas, right? There'll be no net moment of gas. Perfect. Now the question says, Now the question says, if the temperature of one of the container is raised to T2. Now imagine that you are raising the temperature of this temperature. You are using a source. Imagine that you are using a source now. Right? With the help of source, you are maintaining the temperature of this particular chamber to T2. Initially its temperature was Ti. Now you are raising its temperature. If you are raising the temperature of one chamber, that means you are raising the temperature of the gas in the chamber. And if you are raising the temperature of the gas in the chamber, that means pressure of the gas in this chamber will increase. If the pressure of the gas in this chamber increases, there will be pressure difference. Due to the pressure difference, the gases will start intermixing from high pressure to low pressure, unless pressure on both the sides again becomes equal. Unless pressure on both the sides again becomes equal. So finally, after the mixing is done, I'm assuming pressure on both the sides again has become equal, right? Volume here is V, volume here is V. Temperature right here is Ti, and right here it's T2, because you are maintaining it with the help of source. I hope it's clear. So before the arrow, it's before mixing. After the arrow, it's after mixing. Yeah? Do you agree with this? Do you agree with this? So we have increased the temperature of one of the chambers. This part, we are increasing its temperature. So its pressure will increase. There will be pressure difference. And due to pressure difference, the gas will start moving from higher pressure to lower pressure. And finally, the intermixing will stop. There will be no net movement finally, when the pressure on both the sides becomes equal. Okay? So what is the concept which I'll be using? Total moles before mixing has to be equal total moles after mixing. Now, the question is almost done and dusted. Total moles before mixing is, there are some moles of gas here in this container, some moles of gas here in this container. So it's going to be PIV divided by RTI plus PIV divided by RTI. That makes it 2 times PIV divided by RTI. These are the total moles of gas present in both the chambers before mixing. Now after mixing, how many moles of gas in this chamber? Now it's PV divided by RTI. It's PV divided by RTI plus here it's going to be PV divided by RT2. PV divided by RT2, right? So VV everywhere cancelled, RR everywhere cancelled. So this will come out to be 2 times PI divided by TI is equal to, it's going to be P, RR cancelled, right? It's going to be P divided by TI, P divided by T2. So if I take P as common, it's going to be T2 plus Ti divided by Ti T2, correct? So Ti got cancelled. So from this particular equation, I can calculate P from here, and P is going to be equal to 2 times Pi T2 divided by Ti plus T2. This is the final pressure of the gas which you were supposed to calculate as far as the question. Is this clear? I'm not going to give any break. Is this clear, guys? Did you get how do we solve these sort of questions? This is just the calculation. You can check it out afterwards. Right? We're supposed to calculate the final pressure P, and final pressure P after mixing, we did this. Quickly let me know in the chats with the thumbs ups if you got it properly. Properly, guys. Everyone. Everyone means everyone. Arthi, you can drag it a little back, it'll be clear. Guys, everyone quickly in the chats. Quickly. With the thumbs ups, everyone. If I'm saying everyone has to say it, that means everyone has to type it, yes or no. Quickly. Perfect, guys. Now then, if it is clear to everyone, let's move on to something called as Dalton's law of partial pressure. This is again one important statement. One important law. Let's see what exactly this Dalton's law is all about. This is the last part of the ideal gas, okay? After this, we have got the real gas. As far as its statement is concerned, there are some different types of questions which can be asked from this one as well. So understand it carefully, because this is the concept which is used in equilibrium as well when you talk about KP, KC questions, right? Now have a look. As far as this particular statement, if two or more chemically non-reacting gases are enclosed in a vessel, the total pressure of the gaseous mixture is equal to the sum of individual pressures that each gas would exert at same temperature, right? This is the statement. Let's try to understand it. Let's try to understand it. Imagine that, imagine that you have got some three identical containers. Container number 1, container number 2, and container number 3. These are three identical containers which we have, right? Let's assume in the first container you have got ideal gas A, in the second container you have got ideal gas B, right? Let's say there are Na moles of gas A in this container. Let's say volume of gas A over here is V. Let's say the temperature of gas A over here is T. Moles of gas B in this container is Nb, volume is V, and temperature of gas B is T, right? Let's say the pressure of the gas A in this particular container is Pa, pressure of the gas B in this container is Pb. This is something which I'm assuming. Understand properly. Understand properly. Number of moles of gas A in the container, pressure of gas A, volume occupied by gas A, temperature of gas A, right? Number of moles of gas B, volume of gas B, temperature of gas B, pressure of gas B. Now, dear students, since the containers, all the three containers are identical, right? What exactly I'm going to do? I'm going to add these two chemically, these are two chemically non-reacting gases first of all. I'm going to add them up in the same container. I'm going to add them up in the same container. Now, if I ask you, after the addition of these two gases in the same container, how many moles of gases we have in this container? Can I say we have got Na plus Nb moles of gases in this container, right? Since the volume of container again is V only, so the mixture of gas in the container is occupied by the same V volume. The total pressure of the mixture of gas right here, I'm assuming as Pt. Total pressure of the mixture, Pt. Perfect. So basically, over here in this container, what do we have? We have got a mixture of gas. We have got a mixture of gas, mixture of A and B. We have got a mixture of A and B, right? So there was gas A here in the container, gas B here in the container. Now you're mixing them up, right? You got a mixture of gas, right? So in this container, there are total moles Na plus Nb. The total volume occupied with the mixture is V. The temperature of the mixture over here is T, for example, right? What Dalton's law says? Dalton's law states that the total pressure of the mixture, Pt. If I ask you, will the total pressure of the mixture be only due to A, only due to B, or both have contributed towards the total pressure? I must say, both the gases A and B have contributed towards the total pressure, right? And Dalton's law says that the total pressure of the mixture is equal to the sum of contributions made by both the gases. So, contribution made by gas A is, for example, Pa. Contribution made by gas B is, for example, Pb. Contribution made by gas A towards the total pressure of the mixture, that's what you call as partial pressure of A. Contribution made by gas B towards the total pressure of the mixture, that's what you call as partial pressure of gas B. Right? Perfect. Contribution made by gas A towards the total pressure, that's called as partial pressure of gas A. Contribution made by gas B towards the total pressure, that's what you call as partial pressure of gas B. Right? Because in this resulting container, you have got gas A as well as gas B. So there is a mixture of gas here in the container. So total pressure of the mixture has to be equal to the sum of contribution made by both the gases. Right? So initially I had gas A in the container, gas B in the container. Now you are mixing them up. So this mixture contains gas A plus gas B. Correct? And the total pressure of the mixture has to be equal to the sum of the partial pressure. I hope this is clear. Number one. Number two, since I'm assuming gas A is ideal, so let's use ideal gas equation for it. I'll say Pa is equal to Na RT divided by V. Gas B is also ideal. Let's use ideal gas equation. It's going to be Pb is equal to Nb RT divided by V. Correct? Now, total pressure of the mixture has to be equal to Pa is equal to Na RT by V, Pb is equal to Nb RT by V. So take RT divided by V common. it's going to be equal to Na plus Nb, right? It's going to be equal to Na plus Nb. My dear students, from this particular equation, direct question can be asked. Calculate the total pressure of the mixture containing two gases, A and B. It's going to be RT divided by V, Na plus Nb. First, right? Now second. Since PA is equal to Na RT divided by V, if I just do one thing, if I divide PA by PT, let's see what happens. Divide PA by PT. PA is Na RT divided by V and PT is RT divided by V. This is Na plus Nb. Correct? So RT by V cancels out. So what do I get? What do I get here? Let's check it out. What do I get? It's going to be PA divided by PT. PA divided by PT is equal. It's going to be Na divided by Na plus Nb. Na divided by Na plus Nb. So my dear students, this Na divided by Na plus Nb. What is Na? Na means number of moles of A in the container. Nb means number of moles of B in the container. So Na divided by Na plus Nb, do I call it as mole fraction of gas A in the resulting final mixture? Yes, it's mole fraction of A. So finally you got one result. Pa is equal to Pt multiplied by mole fraction of A. So if I ask you from now onwards to calculate the partial pressure of gas A, to calculate the contribution of gas A towards the total pressure of the mixture, this is the relation which we'll be using, right? This is the relation which we'll be using. Similarly, my dear students, if I ask you to calculate partial pressure of B, it has to be equal to total pressure of the mixture multiplied by mole fraction of gas B, right? This is result number 1, this is result number 2, and this has to be result number 3, correct? One more thing, sometimes they might ask you like this. If you write PA divided by PT, if you write PA divided by PT, PA divided by PT, PA by PT, this whole term, this PA divided by PT, what do we call this particular term combinedly as? PA by PT. It's called as, first of all, it is equal to Chi, correct? PA by PT is equal to Chi. I'm just telling you what this PA divided by PT we call as. We call it as the fraction of, it's called as the fraction of total pressure. It's called as fraction of total pressure exerted by gas A. So sometimes they ask you directly a question like this. Calculate the total pressure exerted by gas A. Sorry, calculate the fraction of total pressure exerted by gas A. That means at that time they're asking you this whole term, PA by PT. So basically you have to calculate Chi A value at that time. Sometimes they ask you to calculate the fraction of total pressure exerted by gas B. So that means what do we have to do? Calculate the mole fraction of gas B. That's all, right? So let me summarize all this. Let me summarize all this quickly now. Quickly, I'll summarize all this. For example, this is the container, and this container contains two chemically non-reacting gases. Let's say there are Na moles of gas A, Nb moles of gas B in this container. Let's say volume of this container is V. So the gaseous mixture which we have, since we have got gaseous mixture in this container, so I would say the gaseous mixture over here has occupied the volume V over here. The temperature of the mixture, for example, is T. The total pressure of the mixture is, for example, PT, right? First thing, if I ask you whether the total pressure of the mixture is due to A, due to B, or both have contributed, So total pressure of the mixture is the sum of the contribution made by each, number 1. Number 2, if you want to calculate the total pressure, it has to be equal to RT divided by V, and it's going to be Na plus Nb. In the similar way, if you ask me to calculate contribution made by gas A towards the total pressure of the mixture, it has to be equal to total pressure of the mixture multiplied by Chi A. Contribution made by gas B, it has to be equal to total pressure of the mixture multiplied by mole fraction of gas B, right? This is something which you need to remember. That's it. So let's try to understand this a bit more in detail now. There are some important conclusions which you have to remember. See guys, some basic conclusions. Understand and analyze things. For example, just to make you understand, we have got gas A and gas B in the container. Let's assume number of moles of gas A in the container, or let's say we have got 3 gases, wait. Let's say we have got 3 gases present in container, gas A, gas B and gas C. So first of all, can I say I've got a gaseous mixture? Absolutely, I've got a gaseous mixture. For example, the total pressure of the gaseous mixture is 10 atm. This is the total pressure of the gaseous mixture. Now, this 10 atm won't be only due to A. It won't be only due to B. It won't be only due to C. All would have contributed towards the total pressure, right? Let's say number of moles of A in the container is 2, number of moles of B in the container is 3, number of moles of C in the container is 5. Correct? If I ask you, what is the contribution made by gas A towards the total pressure? It has to be equal to total pressure of the mixture multiplied by mole fraction of A. Total pressure of the mixture is 10 atm multiplied by mole fraction of A means moles of A divided by total moles present in the container. Total moles present in the container. It has to be equal to 10 multiplied by number of moles of A. Number of moles of A, that's 2, divided by total moles present in the container. That's 10. The value exactly comes out to be 2 atm. Correct? 2 atm. Similarly, if you want to calculate PB after solving will come out to be 3 atm. Similarly, PC will come out to be 5 atm. PC will come out to be 5 atm. So what did we calculate? What did we calculate basically? This 2 atm, it is the contribution made by gas A towards the total pressure of the mixture. This 3 atm, it is the contribution made by gas B towards the total pressure of the mixture. This 5 atm, it is the contribution made by gas C towards the total pressure of the mixture. Correct? Now, I want you guys to understand one thing. We had 3 gases in the container. Now tell me, which gas had maximum moles in the container? Gas C had maximum moles in the container. Which gas contributed maximum towards the total pressure? Gas C contributed maximum towards the total pressure. So can I say that gas whose moles in the container will be maximum, that gas whose moles in the container will be maximum, will contribute maximum towards the total pressure? Can we say that? That gas whose moles in the container are maximum will contribute maximum towards the total pressure. Yeah? Perfect. Number 1. Number 2, what was the ratio of the moles of the gases in the container? The ratio of moles was 2:3:5. What is the ratio of the partial pressure of the same gases? 2:3:5. Can I say whatever will be the ratio of the moles of gases in the container, same will be the ratio of their partial pressures? Yeah? Do you agree with all that? Do you agree with all that? Say statement 1. More the moles of gas in the mixture, more will be the contribution towards the total pressure. Statement 2. The pressure of the gases in the mixture is always in the ratio of their moles. I hope both the statements are perfectly clear to every one of you. Right? Let's try to solve a few questions. Let's see if you can do it or not. I'm finding one easy question first of all for you. Okay, the first question. The first question, for example, is like this. Equal masses of H2 and CH4 are present in a vessel. In a vessel. Calculate the fraction of total pressure. Calculate the fraction of total pressure exerted by H2. Exerted by H2 gas. Can you get it right? You have to understand the language. You have to understand the language, guys. See, the question is very simple basically. And the question is like this. Imagine that you have taken a container which contains two gases. One is H2 and one is CH4. You have got equal masses of both the gases. Let's assume that there are x grams of this H2 in the container, and at the same time, there are x grams of CH4 in the container as well. Okay. So if I ask you, how many moles of H2 are there in the container? You'll say equal to mass of H2, molar mass of H2. How many moles of CH4 are there in the container? Mass of CH4, molar mass of CH4. Agreed? Right? Now people, if I ask you to calculate partial pressure of H2, what is the partial pressure of H2? Partial pressure of H2 will be equal to total pressure of the mixture multiplied by mole fraction of H2. So partial pressure of H2 divided by total pressure of mixture has to be equal to mole fraction of H2. Mole fraction of H2 means moles of H2 in the container. This is moles of H2 plus moles of CH4 in the container. Correct? What do we call this term as? This term in particular is called as fraction of. This term in particular is called as this whole term, overall term, it's called as fraction of total pressure. Exerted by what? Fraction of total pressure exerted by H2. It came out to be equal to mole fraction of H2. Mole fraction of H2 means moles of H2, x by 2, whole divided by total moles, which is x by 2 plus x by 16. So x everywhere cancelled. In the numerator, you got 1 by 2. This is 1 by 2 plus 1 by 16. So it's 1 by 2. 16 plus 2 is 18. 18 by 32. 18 divided by 32. So it has to be equal. It has to be equal 1 by 2 multiplied by 32 divided by 18. The value comes out to be 16 divided by 18. So 16 divided by 18, it is basically the fraction of total pressure exerted by what? It is the fraction of total pressure exerted by what? Fraction of total pressure exerted by H2. This kind of a question can be asked. Okay? This kind of a question can be asked. Right? Number one. Number two, for example, you got a question, a very simple question like this. Let's say the question is like this. 20 grams of H2 and 128 grams of O2. 128 grams of O2 are kept in a vessel of 20 liter capacity at 200 degrees centigrade. Calculate the total pressure of the mixture. Simple formula based question. Can you solve it? See guys, the question is something like this. This is a container, and this container, it contains two gases. One is H2 gas and one more is O2 gas. Correct? How many grams of H2 are there in container? 20 grams. That means how many moles of H2 are there? 10 moles. Given mass by molar mass. Similarly, how many moles of O2 are there in the container? Given mass of O2 divided by molar mass of O2, that's 32. The value comes out to be 4. Right? This particular container in which these two gases are there, volume of this particular container is 20 liters. Temperature of the mixture is 200 degrees centigrade, which is 473 Kelvin. What am I supposed to calculate? I'm supposed to calculate the total pressure of the mixture, right? The total pressure of the mixture. 2 minutes back only I told you how to solve it, right? So total pressure of the mixture has to be equal to RT divided by V. This is going to be Na plus Nb, right? So PT is equal to R value is 1 by 12. Volume of the mixture is 20 liters. Temperature of the mixture is 473 Kelvin. Volume of the mixture is 20 liters. Na is 10. N2 is 4. Just solve it. Get the answer in ATM. Every single parameter you have, right? Every single parameter you have. Perfect. Every single parameter you have. I hope all this is clear. Okay. Let's try to have a look on some good questions now. These were some basic questions which I was showing you till now. Complete basic questions. Let's have a look on some good questions. The question is, You have got a container. Let's say this is the container. This container contains two gases, gas A and gas B. Okay. How many moles of gas A are there in container? There are 3 moles of gas A in the container. And how many moles of gas B are there? There are 2 moles of gas B. Correct? 3 moles of gas A and 2 moles of gas B in the container. Well, you have got a gaseous mixture, and the total pressure of the gaseous mixture has been given as 10 atm. Can you let me know how many total moles of gases are there in container? 3 plus 2, 5. Can I say when there are total 5 moles of gaseous mixture in the container, the total pressure exerted by the mixture is 10 atm? Absolutely, I can say that. Right? Total 5 moles. 5 moles of gaseous mixture exert total pressure of 10 atm. Now, if I ask you whether this 10 atm is only due to A, only due to B, or both would have contributed towards 10 atm, I must say both the gases would have contributed towards 10 atm. I hope you agree with the same. Yeah. Now, if I ask you what is the contribution made by gas A towards the total pressure of the mixture, you'll say it's equal to, contribution made by gas A is equal to total pressure of the mixture multiplied by mole fraction of gas A. It's moles of gas A divided by total moles, right? So the value has to be 5152, it's 6 atm. So 6 atm is the contribution made by gas A. Total pressure is 10 atm. Out of 10 atm, 6 atm is contributed by gas A. So how much is contribution made by gas B then? 4 atm. 4 atm is the contribution made by gas B. Or you can use the formula as well, no issues. Correct? Now the question says like this. Now see what the question says. The question says, if 1 more mole of B is added, if you are adding an extra mole of B in the container, if you are adding an extra mole of B in the container, how many moles of B will be there then? Initially you had 2 moles, now you are adding extra mole of B. So 2 plus 1 comes out to be 3. Are you doing some change with the moles of A? No. No, right? Now you tell me one thing. You tell me one thing. How many moles, how many total moles are now there in container? Total, there are 6 moles now in the container, right? Will the pressure of the mixture again be 10 atm? What do you think? The pressure of the mixture again is not going to be 10 atm. Initially, it was 10 atm. When there were total 5 moles present in the mixture, at that time, the total pressure was 10 atm. Now, the total moles are 6. So, moles are increasing. So, will the pressure remain the same? No. Why is that? Because it's mentioned that we have to take temperature and volume constant. If you use the ideal gas equation, PV is equal to nRT, right? Keeping temperature and volume constant. So I'll say pressure is directly proportional to moles, right? At constant volume and temperature, I must say pressure is directly proportional to moles. What does that mean? What does that mean? That means if moles increase in the container, pressure will automatically increase, right? Are the moles increasing from 5 to 6? That means pressure will automatically increase. So how do I get the final pressure? Use the combined gas equation. Since volume and temperature is constant, so I'll be using the formula P1 divided by P2 has to be equal to N1 divided by N2. P1 is given, N1 we have, N2 we have. So P2 will come out to be 12 atm. P2 will come out to be 12 atm. Correct? P2 came out to be 12 atm. Now you tell me, this 12 atm, right? 12 atm is the total pressure. Perfect? 12 atm is the total pressure. Contribution made by gas A towards the total pressure now, how much it will be? Total pressure of the mixture multiplied by mole fraction of A, which is moles of A divided by total moles. The value comes out to be 6 atm. Similarly, contribution made by gas B towards the total pressure is equal to total pressure of the mixture now multiplied by mole fraction of B, moles of B divided by total moles. The value comes out to be 6 atm. Now people, just analyze few things. Just analyze few things. Initially, what was the contribution made by gas A? 6 atm. After the addition of B, what is the contribution made by gas A? It's 6 atm only. So, is there any change in the partial pressure of A after the addition of B? No. I must say, change in the partial pressure of A after the addition of B, that's 0. Right? Change in the partial pressure of A after the addition of B, that's 0. Well, have a look. The partial pressure of B initially was 4 atm. Now, after the addition of B, it's 6 atm. So, has the partial pressure of B changed? Yes. And what is the change in the partial pressure of B? Initially it was 4 atm. Now it's 6 atm. So 2 atm, the change in the partial pressure of B. So what we were supposed to calculate? We were supposed to calculate the change in the partial pressure of A and B. And we got to know the change in the partial pressure of A is 0 and the change in the partial pressure of B is 2 atm. I hope this is clear. Right? Clear to everyone, people? Quickly. Yeah? Yes? Perfectly done? All right. Let's have a look on one more question then. Okay. One question I'm writing over here. 20 grams of H2 and 128 grams of O2 are placed in a vessel of volume 20 liters. Are placed in a vessel of volume 20 liters at 200 degrees centigrade. If an electric spark ignites the mixture, if an electric spark ignites the mixture, calculate the total pressure. Calculate the total pressure of the mixture at the end. Can you give it a try? Can you give it a try? Yes, Bharat, P2 is 12 atm in the last question. It's 12 atm, I know that. Can you give it a try? It's a good question. It is a good question. Quickly. No. No way. See guys, how this sort of a question is to be done. See, first of all, you have got a container. And that container contains H2 gas. And with H2 gas, the container has got O2 gas, right? H2 gas and O2 gas is there in the container. If I ask you how many moles of H2 gas are there in the container, 20 grams of H2 means 10 moles of H2. How many moles of O2 are there in the container? 128 grams of O2 means 4 moles of O2. Now the question is saying, first of all, these two gases, they are placed in a container. Volume of the container we know. Volume of the container we know. How much is that? Volume of the container. We know that. Volume of the container we know that. That's 20 liters. So this is the volume of the container, 20 liters. Temperature is given to us as 473 Kelvin, 200 degrees centigrade. Now, as far as the question is concerned, if an electric spark ignites the mixture, say normally H2 and O2 Under normal conditions, they do not react, right? H2 and O2. Otherwise, there is a lot of H2 in the atmosphere, O2 in the atmosphere. It should continuously rain, right? They should lead to the formation of water. But H2 reacts with O2 in presence of what? In presence of electric spark. So you have to give that activation energy basically. Okay? And here we are giving that electric spark. Since we are giving that electric spark, so there will be a reaction basically. H2 will react with O2 and it will lead to the formation of H2O. So reaction will happen first of all. Since you are providing the electric spark here, so reaction will happen. Right? Reaction will happen. So understand, initially I would say, what will be the state of H2O here? Is it going to be liquid or gas? What do you think? The temperature is kept 200 degrees centigrade. And at 200 degrees centigrade, water automatically will become in gaseous state. Water will be in gaseous state. Okay. Initially, at time t is equal to 0, how many moles of water will be there in the container? 0. Right? Now, do you remember? I have told you, whenever amounts of all the reactants are given to us, which concept do we use? Do we use the limiting region concept? So here I'll be using the limiting region concept. Right? I'll be using the limiting region concept to get to know that after the reaction, what all things will be there in the container. After the reaction, what all things will be there in the container. Correct? Now guys, have a look. First of all, balance the reaction. Balance the reaction. Make it 2 times. Make this 2 times as well. The reaction is balanced. After balancing the reaction, identify the limiting region. Divide the given moles by the respective stoichiometric coefficients. The one whose value comes out to be less, that's going to be the limiting region. So 10 by 2 is 5. 4 by 1 is 4. So O2 is the limiting reagent here. If O2 is the limiting reagent, it would have got completely consumed in the reaction. 0 moles of O2 will be left at the end in the container. Now, entire product will be decided by O2. 1 mole of O2 gives 2 moles of water. So 4 moles of O2 will give me 8 moles of water. So finally, what you'll find? Finally, you will find 8 moles of water in the container. Finally, you will find 8 moles of water in the container. Since this is the limiting reagent, but this is the excess reagent. So there will be some moles of H2 left in the container as well. 1 mole reacts with 2 moles. So 4 moles would have reacted with 8 moles. I had taken 10. Out of 10, 8 have reacted. So 2 moles of H2 will be still left in the container at the end of the reaction. So finally, my dear students, first of all, what happened? You took H2 and O2. You gave electric spark. A reaction happened. Right? A reaction happened. And when the reaction got end, there was no O2 in the container. It got completely consumed. There were only 2 moles of H2 in the container at the end. And there were 8 moles of H2O in the container as well. Right? Now you tell me, at the end, can I say total pressure of the mixture due to O2, that will be 0 because O2 is not there in the container. Right? O2 is not there in the container. O2 is gone, right? O2 is not in the container. Finally, in the container, you will find 2 moles of H2 and 8 moles of water. So total pressure of the mixture will be due to, at the end, total pressure of the mixture will be due to 2 moles of H2 and 8 moles of water, right? O2 has no contribution towards the total pressure of the mixture at the end because it has got consumed. So I can say total pressure of the mixture at the end will be equal to RT divided by V. And it's going to be now number of moles of H2 left in the container plus number of moles of water which would have got formed at the end. So total pressure of the mixture will be equal to R value 1 by 12. Temperature 473 Kelvin. Volume 20 liters. Right? Number of moles of H2 left 2. Number of moles of water formed 8. Just solve it. After solving, you will be getting the value approximately equal to 19 atm. So 19 atm will be the total pressure of the mixture at the end. I hope it's clear to everyone. Got it? Got it, people? Perfectly done? So with this, your ideal gas part is over, right? One part of the chapter is over. That's ideal guess. Now it is the time for the real guess. But I think real guess we are not going to do today because my throat is paining. Okay? Real guess we'll do on Friday or Saturday. Is that cool? In this week, we have to complete stereosomator, right? So the second part of the chapter I'll be doing on Friday or Saturday. My throat is already over. It's in bad condition. Yeah? Perfect. You guys also take it, but do one thing. Revise it again. It's a volatile chapter, okay? You'll forget it afterwards. You will forget it afterwards. Revise it properly. Revise it properly. Again, revise it. I mean, watch it at 2x speed, 2.5x, so that it'll be perfect to you. Okay, I'll share the PDF right after the session. Okay? Right after the session, I'll share the PDF. Rakesh, I've included already this year PYQ. This where one PYQ was asked, that we did already. I think you have joined late. Perfect, guys. So do let me know in the comment section. Did you enjoy the session? Did you like it? Okay. And on which Telegram you'll be getting it? This is the Telegram channel on which you'll be getting the session PDF. t.me/wassim/SIRCHEM. Okay, this is the Telegram channel on which you'll be getting the handwritten PDFs, guys. Okay. Perfect. Okay. Hello guys, do let me know in the comment section if you actually liked the session, if you think the session was beneficial. Okay? So take care. God bless you all. Do let me know in the comment section whatever you have to say. Bye.